There is a place in the universe where time stops, not slows down, not stretches thin, stops, completely, forever. And it is not some distant theoretical curiosity at the edge of creation. It is sitting 26,000 light-years from the chair you are in right now, spinning quietly at the center of our own galaxy. A mouth in space 4 million times the mass of the Sun, massive enough to swallow entire solar systems without leaving a trace. We call it Sagittarius A star. And everything we think we understand about reality, about cause and effect, about the forward march of time itself, falls apart at its edge. For more than a century, physicists have known that black holes should exist. Einstein's equations predicted them. Observations confirmed them. We have photographed their shadows, tracked stars orbiting them at impossible speeds, measured the gravitational waves they produce when they collide. But knowing something exists and understanding what it actually does are not the same thing. Because at the boundary of a black hole, at that invisible line we call the event horizon, the rules break. Light cannot escape. Time dilates to infinity. And if you were to cross that threshold, the universe outside would age billions of years in the seconds it took you to fall inward. This is not science fiction. This is what general relativity predicts will happen. And the most unsettling part is that we have never been more certain of the math and less certain of what it actually means. So what happens when you fall into a black hole? What would you see? What would you feel? And why, after 100 years of studying these objects, do the smartest minds in physics still argue about whether the journey ends in obliteration or something stranger? This is that answer. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. There is something at the center of our galaxy that should not be possible to hide. 4 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit, sitting roughly 26,000 light-years from the chair you are currently occupying. It does not glow. It does not shine. It does not send out light the way a star does. And for most of human history, we had no idea it was there. We named it Sagittarius A star, and it is the supermassive black hole that anchors the Milky Way. Every star in our galaxy, all 400 billion of them, is moving in response to the combined gravity of everything else. But near the center, in a region so dense with stars that the night sky would never go dark, the motion is dominated by one object. An invisible mouth that bends space-time so severely that nothing, not matter, not radiation, not even light itself, can climb back out once it falls past a certain edge. That edge has a name. We call it the event horizon, and it is the point where physics, as we experience it, stops being a useful guide for what happens next. To understand how we found this thing, you have to understand what the center of our galaxy looks like from Earth. If you go outside on a clear summer night far from city lights and look toward the constellation Sagittarius, you are looking toward the galactic core. What you see is a thick band of stars, a bright smear of light stretching across the sky. What you do not see is the center itself. There is too much dust in the way. Thick clouds of gas and microscopic grains block visible light across thousands of light-years of space. If you tried to see the galactic center with an optical telescope, you would see almost nothing. A vague glow, maybe, a sense that something is there. But no detail, no structure, just a wall of obscurity. This is why it took so long to figure out what was happening in there. For most of the 20th century, astronomers knew there was a center. They knew the Milky Way was a spiral galaxy, and spiral galaxies have cores. But what those cores contained, how they behaved, whether anything unusual was going on, all of that was hidden behind the dust. Then radio astronomy came along. Radio waves are much longer than visible light, and they pass through dust clouds almost unbothered. Point a radio telescope at the galactic center and suddenly the fog lifts. You start to see structure, filaments of hot gas, glowing clouds of ionized hydrogen, and right at the very center, a bright, compact radio source that did not behave like a star. The source was discovered in February 1974 by astronomers Bruce Balick and Robert Brown using the baseline interferometer at the National Radio Astronomy Observatory in Green Bank, West Virginia. They were mapping the radio emissions from the galactic center when they noticed something strange. Most of the radio noise was coming from extended clouds and filaments, the kind of messy structure you expect from a busy region full of star formation and supernovae. But there was also a point source, a single compact object sitting right at what appeared to be the dynamical center of the galaxy. It was bright, it was small, and it was not moving. They named it Sagittarius A star to distinguish it from the larger surrounding cloud, which they called Sagittarius A. At the time, no one knew what it was. A dense cluster of stars, maybe. A runaway star formation event, a pulsar, a neutron star. The idea that it might be a black hole was floated early, but black holes in 1974 were still mostly theoretical. The term itself had only been coined a few years earlier by physicist John Archibald Wheeler. There was one confirmed black hole candidate, Cygnus X1, an X-ray source in a binary system where a visible star appeared to be losing mass to an invisible companion. Stephen Hawking was so skeptical that Cygnus X1 was really a black hole that he made a bet with Kip Thorne in 1974. If it turned out not to be a black hole, Thorne would have to buy Hawking a subscription to a certain magazine. If it was a black hole, Hawking would buy Thorne a year of another publication. Hawking conceded the bet in 1990, writing a note in Thorne's office while Thorne was away. Black holes by then had become unavoidable, but Sagittarius A star was not giving up its secrets easily. Radio observations told you where it was and roughly how bright it was, but they did not tell you what it was made of or how massive it was. To figure that out, you needed to watch what it did to the things around it. Gravity is a tell. If something is massive, nearby objects move faster. If you can measure those motions carefully enough, you can work backward to figure out how much mass is pulling on them. The challenge was that the galactic center is 26,000 light-years away. At that distance, individual stars are almost impossible to resolve with a normal telescope. They blur together into a glowing smudge. You need extraordinary resolution, which means you need two things. One, you need to observe in the infrared, where the dust does not block you. Two, you need adaptive optics, a technique that compensates for the distortion caused by Earth's atmosphere by flexing the telescope's mirror in real time. By the mid-1990s, both technologies were finally good enough. Two teams started racing to map the stars near Sagittarius A star. One team was led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany. The other was led by Andrea Ghez at UCLA. Both teams were doing the same thing. They were taking infrared images of the galactic center night after night, year after year, tracking the positions of individual stars as they moved through the crowded core. If Sagittarius A star was just a radio source with no particular mass, the stars nearby would drift slowly, influenced by the combined gravity of all the surrounding material. If Sagittarius A star was something heavy, the stars would move faster. If it was a supermassive black hole, the stars closest to it would be screaming around it at absurd speeds, locked into tight elliptical orbits like planets around a sun. That is exactly what they found. One star in particular, designated S2, orbits so close to Sagittarius A star that it completes a full loop in just 16 years. That might sound slow, but at the distance we are talking about, 16 years is nothing. S2's orbit is smaller than the orbit of Neptune around our Sun, but it is moving at nearly 5,000 kilometers per second at its closest approach. That is more than 1.5% the speed of light. You do not get those kinds of speeds unless something extraordinarily massive is doing the pulling. And whatever is pulling on S2 is sitting right where the radio source is. It is compact, it is dark, and the only object known to physics that can pack that much mass into that smaller space without glowing is a black hole. By the early 2000s, both teams had mapped enough stellar orbits to run the numbers. The orbits fit Keplerian mechanics perfectly, the same math that describes planets around the Sun. You measure the size of the orbit, you measure how long it takes, and you can calculate the mass of the central object. The answer kept coming back the same: 4.3 million solar masses, give or take a few 100,000. The uncertainty comes from not knowing the exact distance to the galactic center down to the last light year, but the core result is rock solid. There is something at the center of the Milky Way with the mass of more than 4 million suns, and it occupies a region of space no larger than the inner solar system. There is no other explanation that works. You cannot pack that much mass into that smaller space with normal matter. A cluster of stars that heavy would collapse under its own gravity within a few million years. A neutron star, the densest stable object known to exist, tops out at about 2 solar masses before it collapses into a black hole. There is no exotic form of matter, no dark matter clump, no quantum field effect that can hold up 4 million solar masses in a region that's small without forming an event horizon. The conclusion is unavoidable. Sagittarius A star is a black hole, not just any black hole, a supermassive one. The term supermassive is not hyperbole, it is a classification. Stellar mass black holes, the kind that form when massive stars collapse at the end of their lives, weigh between a few and a few dozen times the mass of the Sun. Intermediate mass black holes, if they exist, weigh hundreds to thousands of solar masses. Supermassive black holes weigh millions to billions of solar masses. Sagittarius A star sits firmly in that category, and it is not unusual. Most galaxies like the Milky Way have one. Andromeda has one. The Sombrero Galaxy has one weighing in at around 1 billion solar masses. Messier 87, the giant elliptical galaxy in the Virgo cluster, has one clocking in at 6.5 billion solar masses. That is the black hole that the Event Horizon Telescope imaged in 2019, the first direct picture of a black hole's shadow ever taken. Sagittarius A star is not even close to the largest. The current record holder is an object called Tian 618, sitting more than 10 billion light-years away. That black hole weighs roughly 66 billion solar masses. Its event horizon is so large that light would take about 2 weeks to cross from one side to the other. If you dropped Tian 618 into our solar system and centered it where the Sun is, its event horizon would stretch well past the orbit of Neptune. Sagittarius A star, by comparison, is almost modest. Its event horizon has a radius of about 12 million kilometers. That is roughly 17 times the radius of the Sun. Still enormous by human standards, still unimaginably dense. But on the cosmic scale of supermassive black holes, it is a middleweight. What makes Sagittarius A star special is not its size, it is its proximity. 26,000 light-years is nothing in cosmological terms. It is close enough that we can watch individual stars orbit it, close enough that we can track gas clouds as they fall toward it, close enough that when the Event Horizon Telescope finally turned its array of linked radio dishes toward the galactic center in 2017, It was able to resolve the black hole's shadow directly. That image was released in May 2022, and it showed exactly what general relativity predicted: a bright ring of glowing gas surrounding a dark circle. The dark circle is not the black hole itself. It is the photon sphere, the region where light is bent so severely by the black hole's gravity that photons can orbit the event horizon before either escaping or falling in. The ring is the light from gas, heated to millions of degrees as it spirals toward the point of no return. The fact that we can see this structure at all is a miracle of observation. The angular size of Sagittarius A star's event horizon, as seen from Earth, is about 50 microarcseconds. That is the equivalent of seeing a donut on the surface of the Moon. To resolve something that small, the Event Horizon Telescope had to link radio dishes across the entire planet, from Hawaii to Chile to Antarctica, creating a virtual telescope the size of Earth itself. The technique is called very long baseline interferometry, and it works by combining the signals from widely separated dishes to simulate the resolution of a single enormous dish. The data from each telescope is time-stamped using atomic clocks, then flown to a central facility on literal hard drives because the volume of data is too large to transmit over the internet. Processing the data takes months. The result is a single image built from petabytes of radio observations, stitched together with algorithms that have to account for Earth's rotation, atmospheric distortion, and the relative motion of the telescopes themselves. And what that image shows is a black hole, not a hypothesis, not a model, an actual direct observation of the shadow cast by an event horizon. The ring is asymmetric because the black hole is spinning. The side of the disk moving toward us is brighter because the motion of the gas boosts the light in our direction, a relativistic effect called Doppler beaming. The side moving away is dimmer. The shadow itself is larger than the event horizon because the black hole's gravity bends light from behind it, creating a dark region about 2.5 times the size of the actual horizon. That factor of 2.5 comes straight out of the equations of general relativity, and the fact that the observed size matches the prediction is one of the strongest confirmations we have that Einstein was right about how gravity works near the most extreme objects in the universe. But the image is just one piece of evidence. The real proof that Sagittarius A star is a black hole comes from the stars. Decades of tracking their orbits, measuring their speeds, plotting their trajectories, all of it points to the same conclusion. There is an object at the center of the Milky Way that does not emit light, does not reflect light, and has a mass concentration so extreme that general relativity is the only framework that explains it. It is not a cluster. It is not a neutron star. It is not dark matter. It is a singularity surrounded by an event horizon, a place where the known laws of physics compress into a point and stop providing answers. The discovery of Sagittarius A star changed the way we think about galaxies. Before the 1990s, supermassive black holes were considered exotic. Rare objects that might exist in some galaxies but were not a fundamental part of galactic structure. Now we know that is backward. The black hole is not an accident, it is a feature. Almost every large galaxy has one. The mass of the central black hole correlates tightly with the mass of the galaxy's central bulge, the dense region of old stars surrounding the core. That correlation suggests the black hole and the galaxy grew together, feeding off the same reservoirs of gas, influencing each other's evolution over billions of years. Exactly how that process works is still being argued over, but the connection is undeniable. And Sagittarius A star is still teaching us. In 2020, astronomers watched a gas cloud called G2 make a close pass by the black hole. The cloud survived, which was surprising. Many expected it to be torn apart. In 2019, observers detected an unusually bright flare of infrared light from the region immediately around the event horizon, possibly caused by a clump of gas heating up as it spiraled inward. These flares happen irregularly, which tells us that Sagittarius A star is not currently feeding heavily. It is a quiet black hole, at least by the standards of active galactic nuclei. If it were feeding aggressively, the galactic center would be lit up with high-energy radiation, and Earth would be getting bathed in X-rays. Instead, Sagittarius A star is sipping. A few stray gas clouds, the occasional unlucky star wandering too close, but nothing like the violent accretion disks seen around black holes in more active galaxies. That quietness is part of why it took so long to confirm what it was. A feeding black hole is loud. It broadcasts across the electromagnetic spectrum. A starving black hole is almost invisible. The only way we found Sagittarius A star at all was by looking at everything around it and noticing the hole in the middle. The radio emission we detect is not coming from the black hole itself. It is coming from the plasma and magnetic fields swirling around it, heated and twisted by the immense gravitational forces at play. The black hole itself emits nothing. It is a void, a region of space-time so deformed that the usual rules stop applying. Which brings us to the question that sits at the center of everything we are about to talk about. What happens if you fall into one? Not what happens to someone watching you from far away. What happens to you, to your body, to your sense of time, to the light hitting your eyes and the thoughts moving through your brain as you cross the event horizon and head toward whatever waits at the center. That journey starts with understanding what gravity actually is, not a force in the way Newton imagined it, but something stranger. A bending of the stage on which everything moves. Einstein saw it first, and what he saw changed everything. Here is what gravity actually is, and why it took one of the strangest minds in 20th century physics to figure it out. For more than 200 years, gravity was Isaac Newton's domain. In 1687, Newton published the Principia Mathematica, and in it he laid out a simple, elegant framework. Every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. The math was clean, the predictions were accurate. You could calculate the orbit of a planet, the arc of a cannonball, the swing of a pendulum, all with the same set of equations. It worked so well that scientists stopped questioning it. Gravity was a force. It reached across empty space. It pulled things together. Done. But there was a problem, and Newton himself knew it. He had no explanation for how gravity actually worked. How does the Earth reach across 93 million miles of vacuum and pull on the Sun? How does the pull happen instantaneously, as Newton's equations required? He famously wrote that he would frame no hypotheses about the mechanism. He gave us the math, not the reason, and for 2 centuries that was good enough. The equations worked. No one cared about the philosophy underneath. Then, in 1905, Albert Einstein published a paper on special relativity that upended the notion of absolute time. 5 years later, he was working on gravity, and he realized Newton's framework had a fatal flaw. Special relativity said nothing could travel faster than light, but Newtonian gravity required gravitational effects to propagate instantaneously. If the sun suddenly vanished, Newton's equations said Earth would fly off into space at that exact moment, no delay. But according to relativity, Earth should not feel anything until at least 8 minutes later, the time it takes light to travel from the sun to here. Something had to give. Einstein spent the next 5 years trying to build a new theory of gravity that respected the speed limit imposed by relativity. It was not a smooth process. He made mistakes, published incomplete versions, backtracked, and at one point got scooped by the mathematician David Hilbert, who independently derived some of the same equations Einstein was working on. The full theory, general relativity, was finally published in November 1915. It was not an incremental improvement over Newton. It was a completely different picture of what gravity is. Newton said gravity is a force. Einstein said gravity is geometry. Mass and energy do not pull on other objects across space. They warp the shape of space itself, and objects move along the curves that result. This is not a metaphor. This is the actual claim. Space is not a fixed stage on which objects move. It is a dynamic, flexible thing that bends and stretches in response to what is inside it. Time is part of that structure too. Einstein's theory does not treat space and time as separate. It treats them as a single unified fabric called spacetime, and that fabric has geometry. Mass and energy curve it. If that sounds abstract, it is because it is. General relativity is a theory built on tensor calculus and differential geometry, branches of mathematics that most people have never encountered. The equations are notoriously difficult. Even professional physicists often rely on approximations rather than solving them exactly. But the core idea, the thing Einstein realized, can be stated in plain language. Gravity is not a thing reaching across space to pull you down. Gravity is the shape of the space you are moving through. You are not being pulled toward the Earth. You are following the straightest possible path through curved spacetime, and that path happens to bring you downward. The usual way to picture this is with a trampoline or a stretched rubber sheet. Imagine spacetime as a flat sheet. Now place a heavy ball in the middle. The sheet sags. The ball creates a dip, a depression, a well. If you roll a marble near the edge of that well, it will curve inward, spiraling around the heavy ball before eventually falling in or being flung back out, depending on its speed. That is essentially what planets do around the sun. The sun warps spacetime. The planets follow the curves. That analogy gets used constantly in popular science, and it works up to a point, but it also hides something critical. The trampoline is sitting in a gravitational field. The Earth is pulling the ball down, creating the sag. But in the real universe, there is no external force doing the pulling. The curvature of spacetime is not caused by some outside influence. It is the thing itself. The presence of mass and energy directly changes the geometry of spacetime. That change is what we experience as gravity. Here is another way to think about it. Imagine you are standing on the surface of the Earth. From your point of view, you are at rest. You are not moving. But according to general relativity, you are not at rest. You are constantly accelerating upward. The ground beneath your feet is pushing you up, resisting the natural path you would follow through curved spacetime, which is to fall toward the center of the Earth. If the ground were not there, you would follow that path. You would fall. The sensation you call weight, the feeling of the ground pressing against your feet, is not gravity pulling you down. It is the ground accelerating you up, preventing you from following the curve. This is why astronauts in orbit feel weightless. They are not beyond Earth's gravity. They are still well within it, but they are in free fall. They are following the natural curved path through spacetime. And when you are in free fall, you do not feel any force. Einstein called this the equivalence principle. There is no difference between floating in space, far from any mass, and free falling in a gravitational field. Both feel the same, weightless. In both cases, you are following the straightest possible path through spacetime. It is only when something resists that path, like the ground or a rocket engine, that you feel a force. The trampoline analogy also fails to capture time. In general relativity, space-time is not just space, it is space plus time, woven together into a four-dimensional structure. When mass warps spacetime, it warps time as well as space. This leads to one of the strangest and most thoroughly confirmed predictions of the theory. Clocks run at different rates depending on where they are in a gravitational field. The stronger the gravity, the slower the clock. This is not an illusion. It is not a malfunction. It is a real physical effect. Time itself flows at different rates depending on how much space-time is curved around you. This effect is called gravitational time dilation, and we measure it constantly. The global positioning system, the network of satellites that tells your phone where you are, has to account for it. The satellites are orbiting about 20,000 kilometers above Earth's surface. At that altitude, gravity is weaker than it is on the ground. That means the clocks on the satellites run slightly faster than clocks on Earth. The difference is tiny, only about 45 microseconds per day. But if you do not correct for it, your GPS position will drift by kilometers within hours. Every time your phone tells you where you are, it is using math that depends on general relativity being correct. The effect gets stronger the closer you get to a massive object. If you could somehow stand on the surface of a white dwarf, a dead star with the mass of the sun compressed into the size of Earth, your watch would tick noticeably slower than a watch on Earth. If you stood on the surface of a neutron star, a city-sized ball of matter so dense that a teaspoon of it weighs as much as a mountain, your watch would run roughly 30% slower than a clock far from any gravity. And if you got close to a black hole, the slowdown would become extreme. This is the foundation of everything that follows. Black holes are not magical. They are not portals to other dimensions, at least not in the way science fiction likes to imagine. They are regions where space-time is curved so severely that certain predictions of general relativity hit their logical extremes. The equations do not break, they keep working. But the answers they give become so strange that our everyday intuition stops being useful. The math that describes space-time curvature comes from Einstein's field equations, a set of 10 interrelated differential equations that relate the geometry of space-time to the distribution of mass and energy within it. The equations are symmetric, elegant, and hideously complicated. Exact solutions are rare. Most of the time, physicists rely on approximations or numerical simulations, but there are a few cases where the equations can be solved exactly. One of those cases is a spherical non-rotating mass sitting alone in empty space. That solution was found by Carl Schwarzschild in 1916, less than a year after Einstein published the full theory. Schwarzschild was serving in the German army during World War I when he worked out the solution. He sent his results to Einstein, who presented them to the Prussian Academy of Sciences. Schwarzschild died a few months later from an illness contracted on the Eastern Front. He never saw the full implications of what he had discovered. His solution described the space-time geometry around a point mass, and buried in that geometry was a critical radius. If you compressed enough mass inside that radius, something strange happened. The curvature became so extreme that the equations predicted a boundary, a surface where the escape velocity reached the speed of light. Anything inside that surface could not get out, not because it was being pulled by some enormous force, but because every possible future path through space-time led inward. Outward was no longer a direction you could go. That boundary is the event horizon. The term was coined much later, in the 1950s, but the concept was right there in Schwarzschild's solution from the beginning. For decades, most physicists, including Einstein, thought the event horizon was a mathematical artifact, something that showed up in the equations but did not correspond to anything real. Surely, they thought, nature would not allow matter to collapse so completely. There must be some mechanism that stops it. There is not. In 1964, Roger Penrose proved a theorem showing that once a collapsing star crosses a certain point, nothing can stop it from forming a singularity, a point of infinite density where space-time curvature becomes infinite. That theorem, combined with mounting observational evidence, forced physicists to accept that black holes were not just possible, they were inevitable. Any sufficiently massive star that ran out of fuel would collapse into one, and the event horizon was not an artifact, it was real. The radius of the event horizon depends on the mass of the black hole. The formula is simple. Take the mass, multiply by 2, multiply by the gravitational constant, and divide by the speed of light squared. For a black hole with the mass of the Sun, that gives you a radius of about 3 kilometers. For Sagittarius A star, with its 4 million solar masses, the radius is about 12 million kilometers. That is roughly 17 times the radius of the Sun. The event horizon is not a physical surface. There is no shell, no membrane, no wall. It is just a location in space-time, a line you can cross. Once you do, your future is no longer your own. Understanding the event horizon requires understanding how space-time curvature works near a massive object. Imagine you are far from any gravity, floating in empty intergalactic space. Space-time around you is flat. If you throw a ball, it moves in a straight line. If you shine a flashlight, the light goes straight. Time passes at a steady rate. Now imagine you start moving toward a massive object, say a star. As you get closer, space-time begins to curve. The ball you throw no longer travels in a perfectly straight line. It bends toward the star. The light from your flashlight bends too, though only slightly. Your watch still ticks, but if you compared it to a clock that stayed far away, you would find that your watch is running a tiny bit slower. Keep moving closer. The curvature increases. The ball curves more sharply. The light bends more noticeably. Your watch slows further. If the star is dense enough, you can keep getting closer until you reach the surface and the effects stop increasing. But if the star collapses into a black hole, there is no surface to stop you. The curvature keeps increasing. At some point, the bending becomes so severe that light aimed outward gets bent back inward. That point is the event horizon. From the outside, the event horizon looks like a dark sphere, not because it is a solid object, but because no light is coming out of it. Any light emitted inside the horizon stays inside. Light emitted just outside can escape, but it is redshifted, its wavelength stretched by the effort of climbing out of the gravitational well. The closer to the horizon the light is emitted, the more it is redshifted. Right at the edge, the redshift becomes infinite. The light loses all its energy trying to escape and effectively vanishes. This has a strange consequence for anyone watching something fall into a black hole. Imagine you are hovering safely far from the event horizon and you watch a friend fall in. As your friend approaches the horizon, you see them slow down. The light coming from them gets redshifted, shifting toward the red end of the spectrum, then into the infrared, then into radio waves. At the same time, the light takes longer and longer to reach you because it is climbing out of deeper and deeper space-time curvature. From your perspective, your friend appears to freeze just above the event horizon, their image fading and redshifting into invisibility. You never see them cross. Not because they stop, but because the light showing you their crossing takes infinitely long to reach you. But from your friend's perspective, nothing special happens at the horizon. They do not slow down, they do not stop, they do not even notice when they cross. The horizon is not a place where anything physical changes. It is just a point of no return, defined by geometry. Your friend falls through it in finite time according to their own watch. And once they are inside, they keep falling. The only thing that changes is that all their future paths now lead toward the center. Turning around is no longer an option. Not because something is stopping them, but because outward is not a direction that exists anymore inside the horizon. Every direction they can point leads deeper in. This is what general relativity predicts, and the predictions have been tested in every way we can test them. The bending of light around massive objects was confirmed in 1919 when Arthur Eddington measured the positions of stars near the Sun during a solar eclipse. The stars appeared shifted from their usual positions, exactly as Einstein's equations predicted. Gravitational time dilation has been measured with atomic clocks flown on airplanes and placed at different altitudes. The results match the theory. Gravitational waves, ripples in spacetime caused by accelerating masses, were predicted by Einstein and directly detected by the Laser Interferometer Gravitational Wave Observatory in 2015. The waves came from two black holes spiraling into each other and merging, and the signal matched the predictions of general relativity so precisely that it left no room for doubt. Every test we have thrown at general relativity, it has passed. The theory is now more than a century old, and it remains the best description we have of how gravity works. It is not the final word. At extremely small scales, near the singularity at the center of a black hole, general relativity breaks down and quantum mechanics takes over. We do not yet have a theory that unifies the two. But for everything outside the singularity, general relativity works. It tells us what spacetime looks like. It tells us how objects move through it. And it tells us that black holes are not just possible, they are common. Which brings us back to the event horizon, the place where time slows to a stop as seen from the outside. The place where inward becomes the only direction. The place where the rules we live by every day stop feeling like rules and start feeling like suggestions written in a language we are only beginning to learn how to read. That boundary is not a wall you hit. It is a line you cross without noticing, and once you cross it, the universe you came from becomes a memory that can never be revisited. What happens next is not a mystery in the sense that the physics is unknown. The equations still work. But the experience, the subjective sensation of falling past that line and heading toward the center, is something no human will ever report back on. The best we can do is follow the math and see where it leads, and where it leads is strange. The event horizon is not a place you can stand. It is not a surface you can touch. It is not a wall in any sense that your hands would recognize, and yet it is the most absolute boundary in the known universe. Cross it, and every possible future you have left leads to the same destination. The center. Not eventually, not probably, definitely. There is no clever trick, no advanced technology, no exotic propulsion system that changes that outcome. The event horizon is the point where the geometry of space-time itself closes off every exit, not because something is blocking you, because outward stops being a direction that exists. To understand why, you need to understand escape velocity. This is not a new concept. It has been part of physics since long before anyone dreamed of black holes. If you throw a ball into the air, it goes up for a while, slows down, stops, and falls back. Throw it harder, and it goes higher before falling. Throw it hard enough, and it never comes back. The speed you need to throw something so that it escapes a planet's gravity and never returns is called the escape velocity. For Earth, that number is about 11 kilometers per second. For the Moon, it is about 2.4 kilometers per second. The Moon has less mass, so its gravity is weaker, and you do not need to throw as hard to get away from it. Escape velocity depends on two things: how massive the object is and how close you are to its center. The more massive the object, the higher the escape velocity. The closer you are, the higher it gets. If you could somehow compress Earth down to a smaller size without changing its mass, the escape velocity at the new surface would be higher. Shrink it enough, and the escape velocity would eventually reach the speed of light. Shrink it more, and the escape velocity would exceed the speed of light, which means nothing could leave. Not a rocket, not a particle beam, not light itself. That radius, the distance from the center where the escape velocity equals the speed of light, is the event horizon. The calculation is straightforward. Take the mass of the object, multiply it by 2, multiply by the gravitational constant, and divide by the speed of light squared. That gives you the radius. Physicists call it the Schwarzschild radius, named after Karl Schwarzschild, who worked it out in 1916 while serving in the German army during World War I. He derived it from Einstein's equations and sent the result to Einstein, who was initially puzzled by it. The formula is clean. For an object with the mass of our Sun, the Schwarzschild radius is about 3 kilometers, meaning if you could somehow crush the entire Sun down into a ball 3 kilometers across, it would form an event horizon. Everything inside that radius would be cut off from the rest of the universe forever. For Sagittarius, a star, with its 4 million solar masses, the Schwarzschild radius is about 12 million kilometers. That is roughly 17 times the radius of the Sun. Sounds enormous, and by human standards it is. But it is also surprisingly small, given the mass involved. You are talking about packing 4 million suns into a region that light takes about 40 seconds to cross. The density implied by that compression is beyond anything we encounter in everyday life. But here is the strange part. The density at the event horizon itself is not infinite. In fact, for a supermassive black hole like Sagittarius A star, the average density inside the event horizon is actually less than the density of water. You could, in principle, pass through the event horizon of a supermassive black hole and not immediately notice anything wrong. The tidal forces, the stretching and squeezing caused by the difference in gravitational pull from your head to your feet, would be gentle at that scale. You would not be ripped apart, not yet. That is one of the most counterintuitive things about black holes. The bigger they are, the less violent the crossing. A stellar mass black hole, the kind that forms when a massive star collapses, might have an event horizon only a few kilometers across. The tidal forces near that horizon are ferocious. You would be torn apart long before you reached it. But a supermassive black hole has such a large event horizon that the curvature of spacetime near the boundary is actually quite gentle. The gradient is smooth. You could cross the line without feeling a thing. The danger is not at the horizon. The danger is what comes after. The horizon is defined not by density or by tidal forces, but by geometry. It is the surface where the escape velocity equals the speed of light. Since nothing can move faster than light, nothing inside can leave. The reason is not that something is pulling you back. The reason is that spacetime inside the horizon is curved in such a way that all paths, every single trajectory through spacetime that moves forward in time, leads inward. You can point your rocket engines outward and fire them at full thrust, and you will still move toward the center. Not because the thrust is not working, because the direction you are pointing, the one you think of as outward, is not actually away from the center anymore. Spacetime has bent so much that outward and inward have lost their usual meanings. This is hard to picture because our brains did not evolve to think in curved spacetime. We think in terms of flat Euclidean geometry, where straight lines stay straight and directions stay fixed. But inside the event horizon, those rules do not apply. The singularity at the center is not a place in space, it is a moment in time. Once you cross the horizon, reaching the singularity is as inevitable as reaching next Tuesday. You cannot avoid next Tuesday by walking in a different direction. You reach it by waiting. Same thing here. The singularity is in your future, and nothing you do changes that. Before you cross the horizon, though, something else happens, something visible and measurable from the outside. Light does not escape easily from near a black hole. It can escape if it starts far enough out, but the effort costs energy. Light climbing out of a gravitational well gets redshifted. The wavelength stretches. Blue light becomes red. Red light becomes infrared. Infrared becomes microwave. The closer to the event horizon the light originates, the more it gets stretched. Right at the horizon, the stretching becomes infinite. The light loses all its energy trying to get out and effectively vanishes. This is why the event horizon looks black. Not because it is a solid surface absorbing light, because any light trying to leave from that boundary gets stretched into nothingness before it can reach you. This stretching affects everything, not just light. Time itself is part of what gets stretched. Gravitational time dilation is not a new idea. We have talked about it already. Clocks run slower in stronger gravity. The effect is small under normal circumstances, but near a black hole it becomes extreme. If you could hover just outside the event horizon of Sagittarius A star, your watch would tick much slower than a watch held by someone far away. How much slower depends on exactly how close you are. Get close enough, and the difference becomes enormous. A second for you could be years for someone far away. Now imagine you are not hovering. Imagine you are falling. You and a friend start far from the black hole, floating together. You decide to fall in. Your friend stays behind, watching. As you fall closer to the event horizon, your friend sees something strange. You appear to slow down. Not because you are slowing down from your own perspective, you are accelerating, falling faster and faster. But the light coming from you takes longer and longer to climb out of the deepening gravitational well, and the light itself is redshifted more and more as you get closer. From your friend's point of view, you slow down, dim, and redshift. Your image freezes just above the event horizon, fading into the infrared and then into radio waves, and eventually becoming so dim that your friend can no longer detect you at all. This is one of the most famous and most misunderstood aspects of black holes. To an outside observer, nothing ever crosses the event horizon. It just gets stuck there, frozen in time, fading away. But that is not what you experience. From your perspective, nothing strange happens at the horizon. You do not slow down, you do not stop, you do not even notice when you cross. The horizon is not marked by any physical change in your surroundings. It is just a location, a line in space-time. You cross it in a finite amount of time according to your own watch, and once you do, you keep falling. The disconnect between the two perspectives is real. Both are correct. Your friend never sees you cross, and you cross without hesitation. This is not a paradox. It is a consequence of the fact that space-time near a black hole is curved so strongly that different observers, following different paths through space-time, experience time and space in genuinely different ways. There is no single universal now that applies to both of you. Your now and your friend's now diverge. You cross the horizon in your now. Your friend never sees it happen in their now. Both things are true. This has a strange implication. If you could somehow look back at the universe as you fell toward the horizon, you would see the opposite effect. The universe outside would appear to speed up. Stars would age. Galaxies would drift. If you fell slowly enough, hovering closer and closer to the horizon without crossing, you could in principle watch the universe outside age by millions or even billions of years. You would be watching the future unfold in fast forward while barely any time passed for you. That is the flip side of gravitational time dilation. It does not just slow your clock relative to someone far away, it speeds up their clock relative to you. Of course, actually hovering near the event horizon is not easy. To stay in place, you would need to fire rockets constantly, resisting the pull of the black hole's gravity. The closer you hovered to the horizon, the more thrust you would need. Right at the horizon, the required thrust would become infinite. You cannot hover at the event horizon. You can only cross it or stay away from it. There is no in-between. The amount of energy required to hover near a black hole scales with how close you are. Far away, it is manageable. You just need enough thrust to counteract the local gravitational pull, the same way a helicopter hovers by counteracting Earth's gravity. Closer in, the required thrust increases. Near the event horizon, it skyrockets. The acceleration you would need to resist would be measured in millions of times Earth's surface gravity. No known material could withstand that. No rocket we could build could produce that kind of thrust. Even in theory, even ignoring engineering limitations, the energy cost would be staggering. You would be burning fuel at a rate that would exhaust any realistic fuel supply in seconds. That is why everything that gets close to a black hole either falls in or escapes. There is no lingering, no stable orbit exists at the event horizon. The closest stable orbit, the innermost place where you could circle a black hole without falling in or needing to thrust constantly, is farther out. For a non-rotating black hole, the innermost stable circular orbit sits at 3 times the Schwarzschild radius. For Sagittarius A star, that would be about 36 million kilometers from the center. Inside that radius, orbits become unstable. You either spiral inward or you escape. There is no middle ground. This region, between the innermost stable orbit and the event horizon, is where things get messy. Gas and dust falling toward a black hole do not fall straight in. They have angular momentum, a measure of how much they are rotating around the black hole. As they fall, that rotation speeds up, the same way a figure skater spins faster when they pull their arms in. The gas heats up from friction and compression, glowing brightly. This glowing disk of material is called an accretion disk, and it is often the brightest thing in the vicinity of a black hole. The black hole itself is invisible. The disk around it is not. It can outshine entire galaxies. The light from the accretion disk is what the Event Horizon Telescope imaged when it took the picture of Sagittarius A star. The image shows a bright ring of glowing gas surrounding a dark central region. The dark region is not the black hole itself. It is larger than the event horizon. It is the photon sphere, a region where spacetime is so strongly curved that photons, particles of light, can orbit the black hole. Some of those photons escape, creating the bright ring. Some spiral inward and cross the event horizon, disappearing forever. The ring is asymmetric because the disk is rotating. One side is moving toward us, and the light from that side is blue-shifted, boosted in brightness. The other side is moving away, and its light is red-shifted and dimmed. The result is a lopsided ring, brighter on one side than the other. The shadow in the middle, the dark circle, is about 2.5 times the size of the event horizon. That factor of 2.5 comes directly from general relativity. It is the size of the region where any photon aimed in any direction will eventually either fall into the black hole or escape, but none can stably orbit. The edge of that shadow marks the closest light can get to the black hole and still have a chance of escaping. Anything inside that boundary is lost to the outside universe. But let's get back to you. You are falling. You have not crossed the horizon yet, but you are close. What do you see? The universe behind you, the one you are falling away from, appears compressed into a shrinking circle of light. The light from distant stars and galaxies is blue-shifted because you are falling toward the black hole at a significant fraction of the speed of light, and the Doppler effect shifts the light toward shorter wavelengths. The stars in front of you, the ones between you and the black hole, are distorted and warped by the extreme curvature of space-time. Their light is bent around the black hole in strange looping paths. You might see multiple images of the same star, light that took different curved routes through space-time to reach your eyes. Below you, where the event horizon waits, there is nothing, not darkness in the usual sense, more like an absence, a region where no light is coming from. It is not a surface, it does not reflect, it does not emit. It is just the boundary where all the light that was coming from inside has been trapped. The closer you get, the larger it appears. The circle of nothingness grows, swallowing more and more of your field of view, and then you cross it. From your perspective, nothing happens, no jolt, no barrier, no sensation of passing through anything. The event horizon is not a thing, it is a line in space-time, and you cross it the same way you cross any other line. You just keep moving, but now something has changed. You look back, and the universe you came from is still there. You can still see it. Light from outside can still reach you, but you can no longer send light back. Any signal you try to send outward gets bent back inward. You can still see your friend, but your friend can no longer see you. You have crossed into a region of space-time where the future is one way. What happens next is not optional. You are going to reach the center, the singularity, and the closer you get, the stronger the tidal forces become. The difference in gravitational pull between your head and your feet grows. For a stellar mass black hole, this happens almost immediately. You would be torn apart within milliseconds. For Sagittarius A star, you have more time. The tidal forces at the horizon are gentle, but as you fall closer to the center, the gradient steepens. Eventually, even in a supermassive black hole, the forces become lethal. Your body stretches, your molecules stretch, your atoms stretch. This process has a name. Astrophysicists call it spaghettification, and the name is not a joke. You are literally stretched into a long, thin strand, like spaghetti, before being torn apart completely. But before that happens, you would experience something no human has ever experienced. Time itself would behave in ways that are hard to describe. From the moment you cross the horizon, the singularity is no longer a place in space. It is an event in time. It is in your future, the same way tomorrow is in your future. You cannot avoid it by moving. You can only delay it slightly by resisting the infall. But the resistance does not last. The singularity is coming, and nothing stops it. This is where the math stops being comforting and starts being terrifying. General relativity predicts that the singularity has infinite density, all the mass of the black hole compressed into a single point with zero volume, infinite curvature, infinite tidal forces. The equations break down. They stop giving meaningful answers. This is the one place in the universe where general relativity admits it does not know what happens. Physicists expect that quantum mechanics, the other pillar of modern physics, takes over at some point. But we do not have a working theory of quantum gravity yet. We do not know what the singularity actually is. We just know that according to general relativity, it is there, waiting at the center, and once you cross the horizon, you will reach it. But let's not get ahead of ourselves. You have just crossed the event horizon. You are still intact. You can still think. You can still see. And what you see, looking back at the universe you left behind, is about to get very strange. Because now we need to talk about what happens to time when you are inside. Not time as measured by your watch. That still ticks normally. But time as experienced relative to the universe outside. The slowdown you saw approaching the horizon was just the beginning. Now that you are inside, the effects become extreme, and this is where the event horizon earns its reputation as the place where time stops. Not for you, for everyone else. Here is what time does near a black hole, and why the universe you know starts to come apart at the seams. We have already talked about gravitational time dilation. Clocks run slower in stronger gravity. This is not science fiction, this is measured fact. The global positioning system corrects for it every day. Atomic clocks flown on airplanes tick at different rates than clocks left on the ground. The effect is small under normal circumstances, but it is real. Near a black hole, the effect is not small, it is catastrophic. And the closer you get to the event horizon, the more extreme it becomes. This is not a gradual shift, it is a runaway process that ends with something so strange that even physicists who have spent their careers studying it struggle to explain what it means. Let's start with what we know. Time dilation depends on how deep you are in a gravitational well. The stronger the gravity, the slower your clock runs relative to someone far away. Far away means far from any significant mass, floating in empty space where space-time is flat. That is the reference frame. If you take a clock and lower it into a gravitational field, it ticks slower than an identical clock that stayed behind. The effect scales with the strength of the field. On Earth's surface, your watch runs slower than a watch on the International Space Station by about 1 part in 10 billion. Tiny, unnoticeable, without extremely precise instruments. On the surface of a white dwarf, a clock runs noticeably slower, maybe a few parts in 100,000. On a neutron star, the effect is dramatic. A clock on the surface might run 30% slower than a clock far away. That is not a rounding error. That is a clock losing 7 hours for every day that passes elsewhere. Now take that process to its logical extreme. Keep increasing the strength of the gravitational field. Keep getting closer to a more and more compact mass. The time dilation keeps growing. At some point, you reach a place where the clock is running so slowly relative to the outside universe that a second for the clock corresponds to years, centuries, millennia outside. And if you keep going, if you get close enough to the event horizon of a black hole, the dilation becomes infinite. From the perspective of someone far away, the clock stops, not slows down to an imperceptibly slow rate, stops. Time itself, as measured by that outside observer, ceases to advance for anything at the event horizon. This is not a metaphor. This is what the equations say. Take the Schwarzschild solution, the exact solution to Einstein's field equations for a non-rotating spherical mass. Plug in the numbers for a point just above the event horizon. The time dilation factor goes to infinity. A clock hovering at that location, if such a thing were possible, would appear frozen in time to anyone watching from far away. A second on that clock would take literally forever to pass, according to a distant observer's clock. The math is unambiguous. The question is what that means. Here is the setup. You and a friend are floating far from Sagittarius A star, the 4 million solar mass black hole at the center of our galaxy. You are both wearing identical watches, synchronized perfectly. You decide to fall toward the black hole. Your friend stays behind, hovering safely far from danger, watching you through a telescope. As you fall closer, your friend notices something. Your watch appears to be ticking slower than theirs. At first, the difference is subtle, a few microseconds per hour. But as you get closer to the event horizon, the gap widens. Your watch ticks slower and slower. By the time you are a few thousand kilometers from the horizon, your watch is running at half speed from your friend's perspective. 1 second on your watch corresponds to 2 seconds on theirs. You keep falling. The ratio gets worse. 1 to 10, 1 to 100, 1 to 1,000,000. Your friend is now watching seconds pass on their watch while your watch barely advances, and you are still not at the horizon yet. You are just close. The closer you get, the more extreme the dilation becomes. By the time you are within a few meters of the event horizon, your watch appears to have nearly stopped. Your friend sees you moving in extreme slow motion. Your hand, which was waving a moment ago, is now frozen mid-gesture. The light coming from you is redshifted so far into the infrared that your friend can barely detect it. You are fading, slowing, freezing, and then you reach the horizon. From your friend's perspective, you stop completely. Your image is locked in place just above the boundary, dimming and redshifting until it disappears entirely. Your friend never sees you cross. They watch for hours, days, years. You remain stuck at that last moment, a ghost image fading into the background radiation. As far as your friend is concerned, you are frozen at the event horizon forever. Time has stopped for you. You never cross. You never reach the center. You are simply there, suspended at the edge, for all eternity. That is what the outside observer sees. Now let's talk about what you experience. Because the two stories do not match, and that is where things get strange. You are falling. Your watch is on your wrist, ticking normally. 1 second per second. You look at it. The second hand moves. You feel fine. A little nervous maybe, given where you are headed, but physically fine. You are in free fall, so you feel weightless. No force pressing on you. No sense of acceleration. Just a smooth, quiet descent. You look back at your friend, still hovering far above. You see their watch. From your perspective, it appears to be ticking faster, much faster. This is the flip side of time dilation. If their clock looks slow to them when they watch you, your view of their clock is sped up. You see the universe outside aging quickly. Stars are moving. The galaxy is turning. If you fell slowly enough, hovering closer and closer to the horizon without crossing, you could watch billions of years pass outside while barely any time passed for you. But you are not hovering, you are falling. And from your perspective, you reach the event horizon in a finite amount of time, maybe a few minutes, maybe a few hours. Depends on how fast you were moving when you started and exactly what trajectory you followed. But it is a finite time. You cross the event horizon. And when you do, nothing happens. No flash of light, no sudden jolt, no barrier. The event horizon is not a physical thing. It is just a location in space-time. You pass through it the same way you pass through any imaginary line. You just keep moving. So now we have two completely contradictory descriptions of the same event. Your friend says you never cross the horizon. You are frozen there forever. You say you crossed it in finite time, and you are now inside, falling toward the center. Both of you are using accurate clocks. Both of you are applying the correct physics, and yet you are describing completely different outcomes. How is that possible? The answer is that space-time near a black hole is curved so strongly that the concept of simultaneous events stops working the way it does in everyday life. In flat space-time, far from any gravity, it is easy to define what simultaneous means. Two events happen at the same time if they occur at the same moment, according to any observer at rest, relative to both events. Simple. But in curved space-time, especially near a black hole, simultaneity becomes observer-dependent. What counts as now for you does not count as now for your friend. Your timelines, your definitions of present moment diverge. You cross the horizon in your now. Your friend never sees it happen in their now. Both statements are true. There is no universal clock that applies to both of you. Space-time itself is bent in such a way that your experiences of time are fundamentally incompatible. This is not a paradox. It is a feature of general relativity. The theory does not require that all observers agree on what is happening when. It only requires that the laws of physics, the equations themselves, hold in every reference frame. And they do. You follow a path through space-time called a time-like geodesic, the straightest possible path through curved space-time. Your friend, hovering far away, follows a different geodesic. The two paths experience time differently. Your proper time, the time you measure with your own watch, progresses normally. Your friend's proper time progresses normally for them. But the coordinate time, the time assigned to events using your friend's reference frame, does not map cleanly onto your experience once you get close to the horizon. Here is another way to think about it. Imagine spacetime as a grid, a set of coordinates labeling every point in space and every moment in time. Far from a black hole, that grid is nice and regular. The lines are evenly spaced. Time flows smoothly, but near the event horizon, the grid gets warped. The lines stretch and bend. The spacing becomes uneven. If you try to use the coordinates defined by an observer far away, you run into trouble. Those coordinates cannot smoothly cover the event horizon. They break down. The math produces infinities. This does not mean the horizon is not real. It means the coordinate system is bad. You are trying to describe a curved surface with a flat map, and the map fails. There are other coordinate systems that do not break down at the horizon, ones that let you follow a path smoothly across the boundary and into the interior. The Eddington-Finkelstein coordinates, for example, or the Kruskal-Sekaris coordinates. These systems do not have the same problem. In those coordinates, the event horizon is just another place. Time does not stop there. The infalling observer crosses it in finite coordinate time, not just finite proper time. The lesson is that the statement, "time stops at the event horizon," is coordinate dependent. It is true in some coordinate systems and false in others. The physics does not change. The horizon is the same geometric object, no matter which coordinates you use to describe it. But the description changes, and that tells you something important. The idea that time stops at the horizon is not a statement about what the black hole is doing. It is a statement about the limitations of a particular way of describing it. This has philosophical implications that are hard to ignore. If simultaneity breaks down, if there is no universal now, then what does it mean for something to happen? Your friend says you are frozen at the horizon. You say you crossed it and you are falling toward the center. Both of you are right, but those are incompatible claims. You cannot be in two places at once, or can you? The resolution is that you are not in two places at once in any single reference frame. You are in different places depending on whose reference frame you use. From your friend's frame, you are at the horizon. From your frame, you are inside. There is no third frame, no objective view from nowhere that can say which description is the correct one. Both are correct within their own context. This might sound like philosophical word games, but it has real consequences. Consider the question of what happens to information that falls into a black hole. From the outside, the information appears to be smeared across the event horizon, frozen there, encoded in the geometry of the surface. This is part of the basis for the holographic principle, the idea that all the information inside a black hole can be represented as a two-dimensional pattern on the horizon. But from the perspective of someone falling in, the information crosses the horizon and heads toward the singularity. It is not stuck on the surface, it is inside, moving deeper. Both descriptions are used in modern theoretical physics, and they lead to different pictures of what a black hole is. The tension between those pictures has not been fully resolved. Now let's get concrete. What does this time dilation actually look like in numbers? Take Sagittarius A star, 4 million solar masses, event horizon radius about 12 million kilometers. If you could hover 1 meter above the event horizon, which you cannot because the required thrust would be infinite, your watch would run slower than a watch far away by a factor that approaches infinity. 1 second on your watch would correspond to an unlimited amount of time passing outside. If you hovered 10 meters above the horizon, the dilation factor is still enormous but finite. Roughly 1 second for you equals several thousand years outside. Hover 100 meters out and the factor drops, but is still catastrophic. 1 second for you might be a few centuries outside. These are not precise numbers because the exact dilation depends on the detailed geometry and your precise position, but the point is clear. The dilation near the horizon is not a small effect, it is overwhelming. For a stellar mass black hole, the numbers are even more extreme because the horizon is smaller and the curvature is steeper. A black hole with 10 solar masses has an event horizon radius of about 30 kilometers. Hover 1 meter above that horizon and the time dilation is similarly infinite. But because the whole structure is more compact, the tidal forces are also stronger. You would not survive long enough to worry about time dilation. You would be ripped apart by the difference in gravitational pull between your head and your feet. For a supermassive black hole like Sagittarius A star, the tidal forces at the horizon are gentler. You could cross without being torn apart. The time dilation is just as extreme, but at least you are still in one piece to experience it. There is another aspect to this that is worth considering. If time appears to stop at the event horizon for an outside observer, does that mean nothing ever happens inside? If your friend never sees you cross, does the interior of the black hole even exist in any meaningful sense from their perspective? The answer depends on what you mean by exist. The spacetime inside the event horizon is part of the solution to Einstein's equations. It is there in the math. Observers can fall through the horizon and experience the interior. From their perspective, it absolutely exists. But an observer who stays outside can never receive any information from the interior. No light, no signal, no message of any kind can escape. So from the outside, the interior is causally disconnected. It might as well not be there. Events inside cannot affect events outside. The future of the exterior universe does not depend on what happens inside. In that sense, the interior is irrelevant to anyone who stays outside. But here is the twist. Even though the outside observer never sees anything cross the horizon, the black hole still grows. When matter falls in, the mass of the black hole increases. The event horizon expands. The outside observer sees the infalling matter get closer and closer to the horizon, redshifting and dimming, and they see the horizon itself grow to encompass the new material. From their perspective, the matter is added to the horizon, not to the interior. The horizon is not a surface in the usual sense, but it behaves like one from the outside. It has an area. That area increases when matter falls in. It never decreases, at least not in classical general relativity. This is the second law of black hole thermodynamics, and it is strikingly similar to the second law of ordinary thermodynamics, which says that entropy never decreases. The analogy is not a coincidence. Stephen Hawking and Jacob Bekenstein showed in the 1970s that black holes have entropy proportional to the area of their event horizons. They have temperature, they radiate. And the radiation, now called Hawking radiation, carries energy away from the black hole, causing it to slowly evaporate over unimaginably long timescales. But Hawking radiation is a quantum effect. And we are still talking about classical general relativity here. In the classical picture, black holes do not evaporate, they only grow, and the event horizon is a one-way boundary. Things go in, nothing comes out. The question of whether the interior exists is a question about interpretation, not about physics. The physics is clear. There is a region of space-time inside the horizon. Observers can enter it. They experience time and space in that region. The equations describe it. Whether you want to say it exists from the perspective of an outside observer is a matter of philosophy, not science. Now let's think about what this means for causality. Causality is the idea that causes precede effects. If event A causes event B, then A happens before B. This seems obvious. But causality depends on a consistent notion of time. If time is flowing normally everywhere, then before and after have clear meanings. Near a black hole, time does not flow normally everywhere. Different observers have different notions of what before and after mean. For an outside observer, you hovering near the event horizon is an event that happens in their future, getting asymptotically later and later as you approach the horizon. For you, crossing the horizon is an event that happens at a specific moment in your proper time. After you cross, you can look back and see the outside universe, but the outside universe cannot see you. The causal connection is severed. You can receive information from outside. Light from distant stars can still reach you, but you cannot send information back. The flow of causality becomes one way. Inside the horizon, causality gets even stranger. The singularity at the center is not a place. It is an event in time. It is in the future of everything inside the horizon. No matter where you are inside, no matter which direction you are moving toward the singularity. You cannot avoid it. It is as inevitable as tomorrow. And because the singularity is a moment in time, not a point in space, the usual rules about cause and effect start to blur. The singularity is the end of every possible timeline that starts inside the horizon. All paths lead there. There is no path that avoids it. This is not because something is pulling you toward it. It is because the geometry of spacetime inside the horizon is such that forward in time is the same direction as toward the singularity. You cannot move away from it without moving backward in time, which is not possible. This is where general relativity stops giving answers that make intuitive sense. The equations still work. They still describe the geometry, but the geometry itself is so alien to everyday experience that our brains struggle to process it. Time becomes space. Space becomes time. The distinction between the two breaks down, and the singularity, the place where the curvature becomes infinite, is the place where the equations themselves break down. They produce infinities, infinite density, infinite curvature, infinite tidal forces. Those infinities are a signal that the theory has reached its limits. Something else, probably quantum mechanics, needs to take over. But we do not yet have a theory of quantum gravity that works in this regime. So the singularity remains a mystery, but we are getting ahead of ourselves again. You have just crossed the event horizon. You are inside. The singularity is in your future, yes, but it is not immediate. You still have time. How much time depends on the size of the black hole and how fast you are falling. For Sagittarius A star, you might have minutes, maybe an hour, enough time to look around, enough time to think, enough time to realize that the universe you left behind is accelerating away from you in time. You can still see it. Light from outside can still reach you, but the light is now coming from a universe that, from your perspective, is aging rapidly. The stars outside are moving faster. Galaxies are drifting. If you could watch long enough, you would see the universe outside evolve over billions of years while only minutes passed for you. But you will not get to watch that long, because the singularity is coming, and when it arrives, there is no more time, there is no more space, there is only the end. That is what time dilation does at the event horizon. It does not just slow things down, it severs the connection between inside and outside. It breaks the symmetry of time. It creates a boundary where the future of one observer and the future of another observer stop having any overlap. And it does all of this without violating a single equation of general relativity. The theory predicts it. The observations confirm it. The universe allows it. And somewhere at the center of our galaxy, right now, that boundary is there, waiting, quiet, absolute. A place where time, as experienced by the outside universe, does not just slow down, it stops. Not because the clock breaks, Because the geometry of space-time itself has bent so far that time and space have traded roles, and the rules we thought were universal turn out to be local suggestions that only apply when space-time is calm. Which brings us to the next question. What happens when you fall deeper? When the tidal forces start to matter, when the stretching begins, when your body, your molecules, your atoms all start to feel the pull of the center in a way that no structure can resist. That is not about time anymore. That is about geometry. And geometry near a singularity is violent. You have crossed the event horizon. You are inside, and for the moment, you are still you. Your body is intact. Your thoughts are coherent. Your watch is ticking. You can still see the universe you left behind, though it is aging rapidly in your field of view, stars moving through their life cycles, while barely any time passes for you. But none of that matters now, because something else is starting to happen, something you cannot stop. Something that begins gently and ends with your complete destruction. The tidal forces are waking up. Tidal forces are not unique to black holes. You experience them on Earth every day without noticing. The moon pulls on the Earth's oceans with gravity, creating the tides. The side of the Earth facing the moon is pulled slightly harder than the center of the planet, and the far side is pulled slightly less. That difference in pull, that gradient, creates a bulge in the ocean on both sides. High tide. The effect is tiny because the moon is far away and the Earth is relatively small. The difference in gravitational pull between your head and your feet standing on Earth is so small that your body never notices it. But the principle is the same. Tidal forces are the result of gravity varying across distance. One part of an object is pulled harder than another part. If the gradient is gentle, nothing happens. If the gradient is steep, things get pulled apart. Near a black hole, the gradient is not gentle, it is a cliff. And the closer you get to the center, the steeper it becomes. Here is why. Gravity falls off with the square of the distance. Double your distance from a mass, and the gravitational pull drops by a factor of 4. This is Newton's inverse square law, and it still holds in general relativity for weak fields. Near a black hole, the field is not weak, but the principle is the same. The closer you are, the stronger the pull. And because your body has size, because your feet might be a meter or two closer to the center than your head, your feet feel more pull than your head. That difference is the tidal force. And near a black hole, that difference is lethal. Let's put numbers on it. Imagine you are falling feet first towards Sagittarius A star, the 4 million solar mass black hole at the center of our galaxy. You are 2 meters tall. Your head is 2 meters farther from the singularity than your feet. Far from the black hole, that difference is meaningless. The gravitational pull on your head and the pull on your feet are nearly identical. But as you get closer, the difference grows. By the time you are a few thousand kilometers from the event horizon, your feet are being pulled noticeably harder than your head. The difference is still small, maybe a fraction of a percent, but it is there. Your body starts to feel stretched, not painfully yet, just a gentle tension, like someone is pulling on your ankles while you hang from a bar. Keep falling. The gradient steepens. By the time you reach the event horizon, the difference in pull between your head and your feet is significant. Your body is being stretched with a force equivalent to several times your body weight. Uncomfortable, alarming, but not yet catastrophic. You are still intact. For a supermassive black hole like Sagittarius A star, the tidal forces at the event horizon are surprisingly mild. This is because the event horizon is so large, 12 million kilometers across. The curvature of spacetime is extreme, yes, but the gradient, the rate at which the curvature changes over distance, is relatively smooth. You can cross the horizon and survive, at least for a while, but now you are inside, and you are still falling. The singularity is ahead of you in time, not space, but the effect is the same. You are getting closer to the center, and the closer you get, the steeper the gradient becomes. The difference between the pull on your feet and the pull on your head increases. A few times, your body weight becomes 10 times, then 100, then 1,000. Your body is being stretched lengthwise with a force that no muscle, no bone, no tendon can resist. At the same time, you are being compressed horizontally. The tidal force does not just pull you apart along one axis. It squeezes you inward along the other two axes. You are being stretched into a long, thin strand while simultaneously being crushed from the sides. The technical term for this process is tidal disruption. The popular term, coined and popularized by Stephen Hawking, is spaghettification. And the name is not a joke. You are literally being turned into something resembling a strand of spaghetti, long, thin, and utterly destroyed. Hawking described it in his book, A Brief History of Time. He imagined a fictional astronaut falling into a black hole and wrote that the astronaut would be stretched like spaghetti. The image stuck. It is visceral, it is accurate, and it is what happens to anything that gets close enough to a black hole. Your body stretches, your bones elongate and snap, your muscles tear, your skin splits, your cells are pulled apart, your molecules are pulled apart. Eventually, even your atoms are pulled apart. The tidal forces do not stop at the macroscopic scale. They keep working all the way down. By the time you reach the singularity, you are not a body anymore. You are not even matter in any recognizable form. You are a stream of disassociated particles, a thin thread of energy and information falling into a point where the known laws of physics cease to function. This process does not happen instantly. For Sagittarius A star, you might have minutes between crossing the event horizon and being torn apart. For a stellar mass black hole, the timeline is much shorter. A black hole with 10 times the mass of the Sun has an event horizon only about 60 kilometers across. The curvature at that scale is ferocious. The tidal forces are so strong that spaghettification begins before you even reach the horizon. You would be torn apart while still technically outside. Your remains would be stretched into a long, thin stream of particles that spirals inward, crosses the event horizon as a diffuse cloud, and continues falling toward the singularity. From the perspective of someone watching from far away, they would never see you cross. They would just see you pulled into a thin, glowing filament that fades and redshifts into invisibility. From your perspective, you would be dead long before the horizon. The difference between a supermassive black hole and a stellar mass black hole is entirely about scale. A larger black hole has a larger event horizon, and a larger horizon means a gentler gradient at the boundary. The tidal forces are still there, and they still kill you, but they do it more slowly. You get to cross the horizon intact. You get to experience being inside, at least for a few moments, before the forces become unbearable. A smaller black hole does not give you that courtesy. It shreds you on the way in. The end result is the same. You are destroyed. But the path to destruction depends on how massive the black hole is. There is a real-world example of tidal disruption that astronomers have observed directly. In 2019, telescopes detected a bright flare of radiation coming from a galaxy about 215 million light-years away. The flare was designated at 2019 Keys, and it was the closest observed tidal disruption event on record at the time. What happened was this: a star, probably similar in size to our Sun, wandered too close to the supermassive black hole at the center of its galaxy. The black hole's tidal forces tore the star apart. The star did not fall in whole. It was stretched into a long stream of gas. About half of that gas was captured by the black hole and formed an accretion disk, a swirling, glowing ring of matter spiraling inward. The other half was flung outward into space at high speed, expelled by the violence of the disruption. The light from the infalling gas, heated to millions of degrees by friction and compression, lit up the galactic core. Astronomers watched the flare brighten, peak, and then fade over the course of several months as the gas either fell into the black hole or dispersed. This was not a human being falling in, it was a star. A ball of gas weighing about 2 × 10 to the power of 30 kilograms, 200,000 times the mass of Earth, ripped apart like tissue paper. The black hole did not care. The tidal forces do not distinguish between a star and a person. They are just geometry. A gradient in the gravitational field. And anything with size, anything that has one part closer to the center than another part, will feel that gradient. The only question is whether the object is strong enough to resist. Stars are not. Planets are not. Moons are not. Human bodies are definitely not. There is a detail here that is worth pausing on. The tidal forces do not just stretch you, they also compress you. This is less intuitive, but it follows directly from the geometry of curved spacetime. Imagine falling toward a point. As you fall, you are accelerating inward. Your feet are accelerating faster than your head because they are closer. That is the stretching. But you are also falling through space that is curved. The curvature bends your trajectory inward from all sides. Think of it like water draining through a funnel. The water is pulled downward, yes, but it is also squeezed inward as the funnel narrows. Same thing here. The space-time around a black hole is funneling everything toward the singularity. As you fall, you are compressed horizontally while being stretched vertically. Neil deGrasse Tyson described it as being extruded like toothpaste through a tube. The imagery is different from Hawking's spaghetti analogy, but it captures the same process. You are being reshaped by forces you cannot resist. Long and thin. Narrow, a thread. The math that describes this is embedded in the Riemann curvature tensor, a mathematical object that encodes how much spacetime is curved at a given location and how that curvature changes. The tensor has 20 independent components in 4-dimensional spacetime, but the relevant part for tidal forces is the part that describes how geodesics, the paths that free-falling objects follow, spread apart or come together. Near a black hole, geodesics that start out parallel do not stay parallel. They either converge if they are aimed toward the center, or diverge if they are aimed in other directions. An object with size follows multiple geodesics at once, one for each part of the object. If those geodesics are spreading apart, the object gets stretched. If they are coming together, the object gets compressed. Near a black hole, both things happen at once, stretch in one direction, compress in the others. The force you feel is proportional to the gradient of the gravitational field and the size of your body. The bigger you are, the worse it is. The closer you are, the worse it is. For a human-sized object falling into Sagittarius A star, the tidal forces become lethal somewhere between the event horizon and a few thousand kilometers deeper. For a stellar mass black hole, the lethal point is much farther out. For an ultra-massive black hole like Tadden 618, a monster weighing 66 billion solar masses with an event horizon so large that light takes 2 weeks to cross it, the tidal forces at the horizon are almost negligible. You could cross the horizon and not feel anything unusual for a long time. You would have hours, maybe longer, before the tides became dangerous. But eventually, no matter how big the black hole is, you get close enough to the singularity that the gradient becomes infinite and you are destroyed. This raises a question. What happens to the matter after it is torn apart? Where does it go? The classical answer, the one given by general relativity, is that it falls into the singularity. The singularity is not a place in space. It is a point in time, a moment where the curvature of spacetime becomes infinite. All the matter that crosses the event horizon eventually reaches the singularity, not because it is being pulled there by some enormous force, but because every possible path through spacetime inside the horizon leads there. The singularity is in your future, the same way tomorrow is in your future. You cannot avoid it. You reach it by existing. What is the singularity? The equations of general relativity describe it as a point where the density becomes infinite. All the mass of the black hole, every kilogram that ever fell in, compressed into a region with zero volume, infinite density, infinite curvature. The tidal forces at the singularity are infinite. The gravitational field is infinite. Everything becomes infinite, and when that happens, the equations stop working. They do not give meaningful answers. They produce infinities, and infinities are a signal that the theory has reached its limits. General relativity is a classical theory. It does not include quantum mechanics, and at the scales where the singularity lives, quantum effects cannot be ignored. The singularity is the place where general relativity breaks down and something else, some theory of quantum gravity, needs to take over. We do not have that theory yet. Not a complete one. There are candidates, string theory, loop quantum gravity, other approaches, but none of them have been tested experimentally, and none of them make predictions that we can currently verify. The singularity is hidden behind the event horizon, cut off from the outside universe. Nothing that happens there can send information out. We cannot observe it directly. We can only infer its existence from the equations and from the fact that something must be at the center, holding up the event horizon. The singularity is the logical endpoint of gravitational collapse. Once a star or a cloud of gas collapses past a certain point, nothing can stop it. Roger Penrose proved this in 1965 with a theorem that shows singularities are inevitable in general relativity under certain conditions. If you have enough mass concentrated in a small enough region, and if that mass is collapsing, then a singularity will form. The theorem does not tell you what the singularity is, it just tells you that it must be there. Stephen Hawking extended Penrose's work and showed that singularities are not just possible, they are generic. They form in a wide range of situations, not just from collapsing stars, but from the collapse of any sufficiently dense matter. The early universe, in the moments after the Big Bang, might have been a singularity, a point of infinite density from which all of space-time expanded. The Big Bang singularity and the black hole singularity are similar in the sense that they are both places where general relativity predicts infinite curvature and then stops giving answers. The difference is that the Big Bang singularity is in the past. We emerged from it. The black hole singularity is in the future for anything that crosses the event horizon. You fall into it. What does it mean for matter to reach a point of infinite density? Physically, it probably does not mean that. Infinity is a mathematical abstraction. It is what the equations say when you push them beyond their range of validity. Most physicists expect that something happens before you reach true infinite density. Quantum mechanics steps in. At extremely small scales, distances on the order of the Planck length, about 10 to the power of negative 35 meters, space-time itself is expected to become grainy and probabilistic. The smooth geometry of general relativity breaks down and is replaced by something more chaotic. What that something is, we do not know. It might be that the singularity is not a point. It might be a highly curved region of quantum spacetime with no classical description. It might be something we do not have words for yet. There is a deeper problem here. The singularity is not just a place where the math breaks down. It is a place where causality, the idea that effects follow causes in a predictable way, becomes unclear. Inside the event horizon, the singularity is in the future, but it is also the end of all futures. Every timeline ends there. There is no after. Once you reach the singularity, time stops. Not in the sense that it slows down, in the sense that there is no more time coordinate. The singularity is a boundary of spacetime itself. Beyond it, the equations do not describe anything. Some interpretations suggest that spacetime itself ends at the singularity. Others suggest that it continues in some form we cannot yet describe. The truth is, we do not know. This uncertainty is not a failure of physics, it is a signpost. The singularity is telling us that general relativity is incomplete. It is an incredibly successful theory. It has passed every test we have thrown at it. But it is not the final theory. It is a classical approximation that works brilliantly at large scales and weak fields. At the singularity, the scales are not large and the fields are not weak. You are at the Planck scale, the smallest meaningful length in physics, and the fields are as strong as they can possibly be. This is the domain of quantum gravity, and until we have a working theory of quantum gravity, the singularity remains a mystery. Some physicists have speculated that the singularity might not be the end. There are solutions to Einstein's equations, exotic ones, that describe black holes connected to other regions of spacetime. Wormholes, white holes, parallel universes. These solutions are mathematically valid, but they require conditions that probably do not exist in nature. They require negative energy, or exotic matter, or finely tuned initial conditions. Most physicists think they are mathematical curiosities, not descriptions of real objects. But the fact that the equations allow for them at all is intriguing. It suggests that general relativity has more structure than we usually think about. There are pathways through spacetime that are stranger than anything we have observed. But let's be clear, if you fall into Sagittarius A star, you are not emerging in another universe. You are not traveling through a wormhole. You are being torn apart by tidal forces and compressed into a region of spacetime where the laws of physics as we understand them cease to function. That is what the evidence says. That is what the math says. The singularity is not a doorway, it is an end. The process of spaghettification is not instantaneous, but it is inevitable once you are inside the event horizon and close enough to the singularity. The timeline depends on the mass of the black hole, your distance from the center, and how fast you are falling. For Sagittarius A star, once the tidal forces become strong enough to start pulling you apart, the process takes seconds. Your body stretches, your bones snap, your tissues tear. The pain, if you are still conscious, would be unimaginable, but it would not last long. Within moments, you are no longer a coherent structure. You are a stream of particles, and that stream continues to fall. The particles themselves, atoms, then subatomic particles, are eventually pulled apart by the same tidal forces. Electrons are stripped from nuclei. Nuclei are compressed and torn. By the time the stream reaches the singularity, it is no longer matter in any recognizable form. It is energy and information falling into a point where spacetime itself ceases to be smooth and becomes something else. What happens to that information is one of the biggest unsolved problems in theoretical physics, the information paradox. According to quantum mechanics, information cannot be destroyed. The state of a quantum system is always preserved, even if the system is transformed or broken apart. But according to general relativity, anything that falls into a black hole is lost forever. The information is gone, hidden behind the event horizon, inaccessible to the outside universe. If the black hole eventually evaporates through Hawking radiation, as Hawking predicted, then the information might be lost permanently. That would violate quantum mechanics. Physicists have been arguing about this for 50 years. Some think the information is encoded in the Hawking radiation in a way we do not yet understand. Some think it is stored on the event horizon as a kind of hologram. Some think the paradox is telling us that our understanding of space-time at the quantum level is fundamentally wrong. There is no consensus. For you, falling toward the singularity, the paradox is not an abstract question. You are the information, your particles, your quantum state, the configuration of atoms that made up your body and your thoughts. All of that is falling in. From the outside, that information is lost. From your perspective, it is not lost. It is experiencing something. But what that something is, we cannot say. The equations stop. The narrative ends. The singularity is the place where the story runs out of words. But before you reach that point, before the tidal forces become lethal, there is a window. A brief period where you are still intact, still conscious, still able to see. And what you see, looking around you as you fall through the interior of a black hole, is not darkness, it is not nothing. It is the universe, warped and distorted in ways that no human eye has ever seen. The view from inside is the last thing you experience before the geometry takes over and pulls you into threads. And that view, strange as it is something we can describe, not from observation. We have never sent a probe into a black hole, but from the equations, from the math of curved spacetime and the paths that light follows through it. What you would see is not what you expect, and that is where we go next. You have just been pulled into threads, your body, your molecules, your atoms, stretched into a thin stream, falling toward a singularity that exists not as a place, but as a moment in your future. The math says you are destroyed. The equations are clear on that. But before the tidal forces took over, before the stretching began, there was a window. A brief period when you were still whole, still conscious, still able to look around and see. And what the equations predict you would see during that window, the view from inside a black hole as you fall toward the center, is not darkness, it is not nothing, it is something so strange that describing it requires abandoning almost every assumption your brain makes about how vision works. Let's go back. You are falling. You have crossed the event horizon. From the perspective of your friend hovering far above, you are frozen at the boundary, your image fading and redshifting into invisibility. But from your perspective, you crossed the horizon without incident, no flash of light, no barrier, no sensation of anything unusual. The event horizon is not a physical surface. It is just a location in space-time where the geometry changes in a way that makes escape impossible. You passed through it the same way you passed through any imaginary line. You just kept moving. And now you are inside. The first thing to understand is that being inside does not mean you are surrounded by walls. There is no shell, no membrane, no boundary you can see or touch. The event horizon is behind you now, but it is not visible as a surface. It is not glowing. It is not marked in any way. If you tried to look back at it, you would not see a line drawn across space. You would see the universe, stars, galaxies. The same sky you saw before crossing, though heavily distorted. Light from outside can still reach you. Photons from distant stars are still traveling through the black hole's gravitational field, bending and curving as they fall, and some of those photons are hitting your eyes. The event horizon is a one-way membrane for light, but the one-way rule only applies to light trying to leave. Light from outside can come in just fine, so you can still see the universe you left behind, at least for a while. But the view is not normal, not even close. The light reaching you has been bent by the extreme curvature of space-time around the black hole, and the closer you are to the center, the more severe the bending becomes. This is gravitational lensing, the same effect that makes distant galaxies appear warped and magnified when observed through the gravitational field of a massive galaxy cluster. Einstein predicted it. Astronomers use it. Near a black hole, the effect is so strong that it stops being a subtle distortion and becomes the dominant feature of what you see. The universe does not look like a sphere of stars surrounding you. It looks compressed, folded, multiplied. Light that would normally travel in straight lines is now taking curved paths through spacetime, and those paths loop and spiral in ways that create visual effects your brain was never designed to process. Here is what happens. Imagine you are falling feet first toward the singularity. You look up, back toward the universe you came from. The stars and galaxies in that direction are still visible, but they are squeezed into a shrinking circle of light. This is because space-time around the black hole is so strongly curved that light from a wide range of directions gets focused and compressed. The technical term is relativistic beaming, though that usually refers to something slightly different. The principle is the same. Light from a large region of the sky is being funneled into a smaller and smaller area of your field of view. The circle of the universe behind you, the part of the sky where the stars still look more or less normal, is getting smaller. Everything else, the sky to your sides and below you, is filling with something stranger. Below you, in the direction you are falling, there is no light coming from the singularity. The singularity is not an object. It is not glowing. It does not emit anything. It is a point where space-time curvature becomes infinite and the equations stop working. From your perspective, it is in your future, not in the space ahead of you, but the visual effect is the same. The region of sky in that direction is dark, not black in the sense of a dark surface, more like an absence, a void where no photons are arriving because there is nothing there to emit them, and no path for external light to take that would let it reach your eyes from that direction. The singularity is invisible. What you see in that direction is nothing, but to the sides, the view gets complicated. Light from stars and galaxies that are physically located far to your left or right, or even behind you, can reach you by taking curved paths through the black hole's gravitational field. Space-time is so warped that photons can spiral around the black hole multiple times before reaching your eyes. This creates the possibility of seeing the same object in multiple places. A star that is actually behind you might appear in front of you, its light bent around the black hole. You might see it twice, 3 times, more, depending on how many loops the light takes before it reaches you. Each loop corresponds to a different path, and each path arrives at your eyes from a different angle, creating multiple images. This effect is well understood mathematically. Physicists have run the calculations. They have simulated the paths that light takes near a black hole using the equations of general relativity. The simulations show that the view from inside is dominated by extreme distortion and multiplication of images. The outside universe does not surround you in a simple sphere. It is wrapped around you in layers, folded and compressed into a complex pattern that shifts as you fall. The closer you get to the singularity, the more compressed and distorted the view becomes. The circle of the outside universe shrinks, the dark region below you grows, and the light from the universe behind you starts to show up in strange places, bent into arcs and rings by the curvature of space-time. One of the most famous predictions is that you might be able to see the back of your own head, not because there is a mirror, because light from your head can travel outward, loop around the black hole along a curved path, and return to your eyes. This is not science fiction. This is what the equations predict. The path exists. Whether you could actually resolve the image clearly enough to recognize it as the back of your own head is another question. The light would be extremely redshifted and distorted. It might arrive as a faint smeared glow rather than a sharp image. But in principle, the photons that left the back of your head a moment ago could reach your eyes after taking a curved route through the black hole's gravitational field. The same goes for anything else nearby. You could see multiple images of your own body, your spaceship if you had one, or any other object falling with you. Each image corresponds to a different number of loops the light took on its way to your eyes. The bending of light near a black hole is so extreme that the usual rules of perspective stop applying. Normally, objects farther away look smaller. That is because the angle they take up in your field of view decreases with distance. But near a black hole, light paths curve in ways that can make distant objects appear larger or closer than they should. A galaxy that is billions of light years away might appear magnified and stretched into an arc or a ring, its light bent around the black hole in a way that amplifies its apparent size. This is the same gravitational lensing effect that astronomers observe when looking at distant galaxies through the gravity of a foreground cluster. But when you are inside the black hole, you are not just seeing lensing of distant objects. You are seeing the entire universe lensed and distorted by the black hole you are inside. The effect is all-encompassing. There is no direction you can look where the view is undistorted, and the distortion is not static. As you fall deeper, the geometry around you changes. The circle of the outside universe continues to shrink. The dark region grows. The patterns of light shift and twist. If you could somehow survive long enough to watch the process unfold, you would see the universe you came from compressed into a smaller and smaller patch of sky, eventually collapsing into a single bright point directly above you. All the light from the entire observable universe, every star, every galaxy, every photon that was able to reach you, funneled into one spot. And then, as you reach the singularity, even that point disappears. Not because the light stops coming, because time stops. Your timeline ends. The singularity is the end of your proper time, the moment when the curvature becomes infinite and the equations cease to describe anything. What happens after that is not a question physics can currently answer, but let's slow down. You have not reached the singularity yet. You have just crossed the event horizon. You are still falling, and one of the most disorienting aspects of the experience is that your sense of direction stops making sense. Normally, when you fall, you know which way is down. Down is toward the thing pulling you, the earth, the floor, the center of gravity. But inside a black hole, the concept of down becomes ambiguous. The singularity is not below you in space. It is ahead of you in time. You are not falling toward a place. You are falling toward a moment. And every direction you can point, every possible trajectory through space, leads to that same moment. You cannot avoid it by turning. You cannot escape it by firing rockets in the opposite direction. The singularity is in your future, and nothing you do changes that. It is as inevitable as next Tuesday. This is one of the hardest things to wrap your mind around because it violates every intuition you have about motion and direction. If you are in a car heading toward a wall, you can turn the wheel, you can swerve, you can avoid the wall. That is because the wall is a location in space, and space has multiple directions. You can choose one. But inside the event horizon, the singularity is not a location in space. It is a point in time, and time only moves in one direction. You experience that direction as forward, as the passage of moments, but geometrically, forward in time is the same as toward the singularity. The two are equivalent. You reach the singularity by existing, by continuing to experience time. There is no swerve that helps. The equations describe this using a coordinate system that maps spacetime inside the event horizon. In those coordinates, the radial direction, the one that points toward or away from the center in normal space, becomes time-like, and the time direction becomes space-like. This is not a trick of math, it is a real change in the structure of space-time. The roles of space and time swap. Inside the horizon, moving inward is not a choice you make about where to go. It is a consequence of time moving forward. You move inward because time passes. The singularity is not ahead of you in the sense that you can see it and move toward it. It is ahead of you in the sense that it is later. It is the next thing that happens. And nothing stops time from moving forward, not even you. This swapping of roles is what makes the event horizon a point of no return. It is not that something is pulling you so hard you cannot escape. It is that the geometry of space-time has changed in such a way that escape is not a direction anymore. Outward, the direction that would take you back through the event horizon and into the outside universe, is no longer a direction you can move in without traveling backward in time. And traveling backward in time is not possible. So outward is not available to you. Every path through space-time that moves forward in time, every possible future you could experience, leads inward toward the singularity. That is why nothing escapes, not because the black hole is holding it. Because the structure of space-time inside the horizon does not allow for outward trajectories. Now let's talk about speed. You are falling. How fast? From your perspective, your own clock is ticking normally, 1 second per second. You feel weightless because you are in free fall. There is no force acting on you. You are following the natural path through curved space-time, the same way a planet follows its orbit around a star. No thrust, no resistance, just motion along a geodesic. But your speed, as measured relative to the singularity or relative to the center of the black hole, is accelerating. You are falling faster and faster. By the time you are close to the singularity, you are moving at a significant fraction of the speed of light. And as you approach the singularity itself, your speed relative to nearby particles or nearby bits of space-time approaches the speed of light. Not because something is pushing you, because the geometry is pulling you along a path that accelerates. The closer you get to the singularity, the shorter your remaining proper time becomes. Proper time is the time you measure with your own watch, the time you experience. For a black hole like Sagittarius A star, with 4 million solar masses, the proper time from the event horizon to the singularity is measured in minutes, maybe 20, maybe 30, depends on the exact trajectory you followed and how fast you were moving when you crossed the horizon. But it is a finite time. A clock on your wrist would tick through those minutes normally, each second feeling like a second, and then you would reach the singularity. That is how long you have, less than an hour. And during that time, the tidal forces are growing, the stretching is starting. The pain, if you are still conscious, is becoming unbearable. But you are also watching the universe behind you compress into a point of light. Both things are happening at once. For a stellar mass black hole, the timeline is much shorter. A black hole with 10 times the mass of the Sun has an event horizon only about 60 kilometers across. The proper time from the horizon to the singularity is measured in milliseconds. You would not have time to see anything. You would not have time to think. The tidal forces would tear you apart before you even had a chance to process what was happening. The experience would be over almost as soon as it began. For a supermassive black hole, you get more time. Enough time to look around. Enough time to realize what is happening. Enough time to regret your decision to fall in, assuming you had a choice. There is another effect worth mentioning. As you fall, the light from the universe behind you is not just distorted, it is also blue shifted. This is the Doppler effect. You are moving toward the source of the light at a significant fraction of the speed of light, and that motion shifts the wavelength of the light toward shorter wavelengths. Red light becomes blue, Blue becomes ultraviolet. Ultraviolet becomes X-rays. If you were falling fast enough, the light from ordinary stars behind you would be shifted so far into the high-energy end of the spectrum that it would become dangerous. Gamma rays, hard enough to kill you. Not that it matters at this point, because the tidal forces are also killing you. But the point is that the light you see is not just warped, it is also shifted in frequency. The universe behind you glows brighter and bluer as you fall faster. And there is one more twist. As the light from the outside universe gets compressed into a shrinking circle above you, the intensity increases. The same amount of light is being focused into a smaller area. That makes it brighter, much brighter. Some simulations suggest that the final moments before you reach the singularity would be visually dominated by a single intensely bright point of light directly overhead, glowing with the combined luminosity of every visible object in the universe. Blue shifted into the X-ray or gamma ray range and compressed into a region smaller than the full moon. That point would be the last thing you see, not the singularity. The singularity is invisible. The last thing you see is the universe you left behind, crushed into a single blinding point of light, and then nothing. This description is based on numerical simulations and exact solutions to the equations of general relativity. Physicists have worked out what the light paths look like. They have traced the geodesics. They have calculated the red shifts and blue shifts. They have modeled the visual appearance of the sky as seen by an observer falling through the event horizon and toward the singularity. The predictions are consistent. The view is dominated by extreme distortion, compression of the external universe into a shrinking circle, and multiplication of images due to light taking multiple looping paths through curved spacetime. There is no ambiguity in the math. The open question is whether a human could actually perceive any of this before being torn apart or before losing consciousness from other effects. Probably not. The timeline is too short. The forces are too strong. But the equations say this is what would be there to see if you could somehow survive and keep your eyes open. One detail that often gets glossed over is that the view depends on where you are looking. If you look back toward the event horizon, toward the outside universe, you see the compressed, distorted sky. If you look to the sides, you see multiple images of the same objects, light that has looped around the black hole. If you look ahead, toward the singularity, you see darkness. Not because the singularity is a black surface, because there is no light coming from that direction. The singularity has not emitted anything. It is not a source, it is a sink. Everything falls into it, nothing comes out. So the region of sky in that direction is empty, a void. And as you fall deeper, that void grows. It takes up more and more of your field of view. Eventually, it dominates. The darkness below you expands until it fills almost everything, leaving only a small bright circle above where the universe used to be. There is a concept in general relativity called the photon sphere. This is a region just outside the event horizon where the curvature of spacetime is so strong that photons can orbit the black hole in circular paths. Light traveling at exactly the right distance from the center can loop around indefinitely, never falling in and never escaping. The photon sphere is unstable. Any small perturbation will cause the light to either spiral inward or escape outward. But for a brief moment, light can circle the black hole. The photon sphere is the source of some of the visual effects you see when falling in. Light from the outside universe can skim along the photon sphere, looping partway around the black hole before either escaping or falling inward. If it falls inward and reaches your eyes, you see a distorted image of something that is actually far to the side or even behind you. The photon sphere acts like a lens, bending light into paths that would not exist in flat spacetime. The view from inside the photon sphere, which is where you are once you cross the event horizon, is even stranger. Light can take multiple complete loops around the black hole before reaching you. Each loop adds to the complexity of the image. You might see a star not just twice, but 3 times, 4 times, as many times as there are distinct paths the light can take from the star to your eyes. Each path corresponds to a different number of orbits around the photon sphere. The paths farther from the sphere are less curved and arrive at your eyes from angles closer to the true direction of the star. The paths closer to the sphere are more curved and arrive from angles that are completely different. The result is a layered, multiply-imaged sky where every object you can see is duplicated in strange places. Your brain tries to make sense of it and fails. The visual system evolved to interpret light traveling in straight lines. Here, nothing is straight. Everything is curved, looped, folded. The image is incomprehensible, and all of this is happening while you are also experiencing time dilation relative to the outside universe. From your perspective, your watch ticks normally. But if you could somehow look at a clock that stayed outside the event horizon, you would see it ticking faster, much faster. The universe outside is aging rapidly relative to your proper time. If you fell slowly enough, hovering near the horizon for an extended period before finally crossing, you could watch centuries pass outside while only minutes passed for you. This is the flip side of the effect your friend sees. They see you frozen, you see them sped up. Both views are correct within their own reference frames. There is no contradiction. Spacetime is curved, and curved spacetime allows for these kinds of perspective-dependent effects. But you are not hovering, you are falling, and the timeline is short. Within minutes of crossing the horizon, you reach the singularity. The view collapses. The bright circle of the universe above you shrinks to a point. The darkness below expands to fill everything, and then the curvature becomes infinite. The tidal forces become infinite, and your proper time ends. That is the prediction. That is what the equations say happens. Whether the prediction is exactly correct, whether quantum mechanics changes the story at the very end, we do not know. General relativity breaks down at the singularity. The infinities in the math are a signal that the theory has reached its limit. Something else takes over, and that something is not yet part of our established physics. But the visual experience of falling through the interior of a black hole is something general relativity can describe, and the description is clear. The universe you came from does not disappear. It stays visible, compressed and distorted, shrinking into a smaller and smaller region of your field of view as you fall. The singularity ahead of you is invisible, a growing void that eventually swallows everything. The light paths loop and bend in ways that create multiple images of the same objects. The intensity and frequency of the light shift as you accelerate, and the entire process unfolds in a few minutes of your proper time, during which the outside universe ages by an amount that depends on how close you were to the horizon and how long you hovered there before crossing. It is a one-way journey. There is no going back. And the destination is not a place. It is a moment, the last moment, the point where your timeline ends and the equations stop giving answers. Which brings up a question that physicists have asked for decades. If nothing can escape from a black hole, if the singularity is the end of every timeline that crosses the horizon, then what happens to the information? Quantum mechanics says information is never destroyed. General relativity says everything that falls into a black hole is lost. One of those statements must be wrong, or our understanding of both theories is incomplete. The information paradox is unresolved. Some think the information is encoded on the event horizon in a holographic form. Some think it is released slowly through Hawking radiation in a scrambled form that we do not yet know how to decode. Some think the paradox is telling us that space-time itself is an approximation that breaks down under extreme conditions. There is no consensus. But the paradox is real, and it is one of the clues that the singularity is not the end of the story. There is something beyond it, some structure or process or phenomenon that we do not yet have the tools to describe. And that is the view from inside, not darkness, not nothing. A universe warped and compressed and multiplied, a sky that folds in on itself, light taking paths that loop and spiral through space-time in ways that your brain cannot pass, a growing void where the singularity waits, and a final blinding point of light as the universe you left behind collapses into a single spot above you. That is what the math predicts you would see if you could survive the journey long enough to see anything at all. It is not comforting, it is not reassuring, but it is what the equations say. And the equations, tested and confirmed across a century of observation and experiment, have earned the right to be taken seriously. The view from inside a black hole is not a mystery in the sense that we have no idea what it would look like. We have an idea. We have detailed models. We have simulations. What we do not have is a way to test it, and we will never have a way to test it, because nothing that crosses the event horizon can send information back. But the equations do more than describe the interior. They also suggest that black holes might not be the only strange objects general relativity allows. There are solutions to Einstein's equations that describe things even stranger than black holes, objects that are the time reverse of black holes, regions where nothing can enter but everything can leave, tunnels through space-time that connect distant points or even distant universes. These solutions exist on paper. Whether they exist in reality is another question, but the fact that the math allows for them at all is intriguing. It hints at a universe richer and stranger than the one we see, and it raises the possibility that black holes, as strange as they are, might be the gateway to understanding something even stranger, something that exists not as an endpoint, but as a passage, a bridge, a shortcut through the fabric of space-time itself. The equations describe white holes, not as science fiction, not as metaphor, as actual solutions to Einstein's field equations, solutions that are every bit as mathematically valid as the ones that describe black holes. The difference is that no one has ever seen one, no telescope has detected one, no observation has even hinted that they might exist. And most physicists, if you corner them and ask directly, will tell you they probably do not. But the math does not care what physicists believe. The math says white holes are possible. And if the math says something is possible, we need to understand what it is saying and why the universe might have chosen not to build one. A white hole is the time reverse of a black hole. That phrase gets thrown around constantly, but it is worth unpacking because it is both precise and deeply strange. A black hole is a region of space-time where things can enter but nothing can leave. The event horizon is a one-way boundary. Cross it going inward and you are trapped. Every possible future path through space-time leads deeper toward the singularity. Outward is not a direction you can move in without traveling backward in time, which is not allowed. That is what makes a black hole a black hole. It is a trap. Once you are in forever, at least from your own perspective. The universe outside never sees you cross, but you cross, you fall, you reach the singularity. End of story. A white hole is the opposite. It is a region of space-time where things can leave but nothing can enter. The boundary, still called an event horizon, though the name feels wrong, is a one-way surface pointing the other direction. You cannot cross it going inward. You can only cross it going outward. If you tried to fall into a white hole, you would be repelled, not by a force, not by some kind of barrier, by the geometry of spacetime itself. The structure of spacetime inside a white hole is such that every possible path through it, every geodesic, every trajectory that moves forward in time, leads outward. Inward is not a direction that exists for anything inside. Just like a black hole traps everything, a white hole expels everything. Matter, energy, light, information, all of it comes out, none of it goes in. This is not a new idea. The white hole solution was found almost as soon as physicists started analyzing black holes seriously. In the 1930s, Robert Oppenheimer and Hartland Snyder were working out what happens when a massive star collapses. They derived the black hole solution, the one that describes an object so dense that it forms an event horizon. But the equations of general relativity are time-symmetric. If you take a solution that describes matter collapsing inward and you reverse the direction of time, you get a solution that describes matter exploding outward. That reversed solution is a white hole. Oppenheimer did not call it that. The term came later, probably in the 1960s, when physicists started taking the idea more seriously. Igor Novikov, a Russian cosmologist, wrote about white holes in 1964, and the concept became part of the standard toolkit for thinking about exotic spacetime geometries. The math is clean. You take the Schwarzschild solution, the simplest exact solution to Einstein's equations that describes a non-rotating black hole, and you extend it. The Schwarzschild solution has two regions. One is the exterior, the normal universe where we live. The other is the interior, the region inside the event horizon where everything falls toward the singularity. But if you look at the full mathematical structure of the solution, not just the parts that seem physically relevant, you find two more regions. One is a second exterior, a mirror copy of our universe on the other side of the black hole. The other is a white hole, a region where the singularity is in the past instead of the future, and everything is being expelled rather than sucked in. These four regions are connected by a structure called a wormhole, a tunnel through spacetime that links the black hole and the white hole. This is the Schwarzschild wormhole, sometimes called the Einstein-Rosen bridge, after Albert Einstein and Nathan Rosen, who explored this geometry in 1935. The picture it paints is striking. You have a black hole in our universe. You have a white hole in another universe, or another part of our universe, and connecting them is a tunnel. Matter falls into the black hole, travels through the tunnel, and emerges from the white hole, a shortcut, a passage, a bridge between distant regions of spacetime. The problem is that the bridge does not work, at least not in the way most people imagine when they hear the word wormhole. The Schwarzschild wormhole is not traversable. The tunnel pinches off too quickly. If you tried to travel through it, you would not make it. The geometry of the tunnel is such that it closes before anything, even light, can pass from one end to the other. You fall into the black hole, you start moving through the tunnel, and the tunnel collapses around you. You never reach the white hole, you hit the singularity instead. The singularity is not at the center of the black hole in this picture. It is in the middle of the tunnel, a barrier that cuts the black hole off from the white hole. Nothing gets through. This has been known since the solution was first analyzed in detail. The Einstein-Rosen bridge is a mathematical structure, not a physical passage. It connects two regions of spacetime, yes, but the connection is not usable. You cannot send a probe through it. You cannot send a signal through it. You cannot travel through it. The singularity blocks the way, and the singularity is a place where the equations break down and spacetime itself ceases to have a smooth structure. That is the first reason why white holes and wormholes are not part of mainstream astrophysics. They are solutions to the equations, but they are not solutions that describe anything we can observe or interact with. The second reason is more fundamental. There is no known physical process that would create a white hole. Black holes form when massive stars collapse. The process is well understood. The star runs out of fuel. The core collapses under its own gravity. If the core is massive enough, more than about 2 or 3 solar masses, nothing can stop the collapse. The core forms a singularity and an event horizon, a black hole. We have observed this process. We have detected the gravitational waves produced when black holes form from collapsing stars. We have watched stars spiral into black holes and disappear. Black holes are real. They form naturally. They exist in the universe. White holes do not, or at least we have no evidence that they do, and no theory that explains how they would form. A white hole is a time-reversed black hole. That means it would have to start as a singularity that already exists and then explode outward, ejecting matter and energy. But where does the singularity come from? What creates it? A black hole forms from a collapsing star. A white hole would have to form from nothing, or from some pre-existing singularity that has been sitting there waiting to explode. That is not how the universe works, as far as we can tell. The laws of physics do not allow for matter to spontaneously organize itself into a dense singularity and then burst outward. Entropy does not decrease. Disorder does not reverse. White holes are thermodynamically implausible. Some sources describe this in blunt terms. A white hole would represent a local decrease in entropy. It would be a region of spacetime where order increases and chaos decreases, which violates the second law of thermodynamics. Not absolutely, because thermodynamics is statistical and local violations are technically possible, but overwhelmingly unlikely. A white hole would also be unstable. Any stray particle or photon in the surrounding space would try to fall into it, but the white hole cannot accept infall. The geometry forbids it. The particle would be reflected, bounced back by the structure of spacetime. That reflection would carry energy, and the energy would have to come from somewhere. The most likely result is that the white hole would interact with the ambient radiation in the universe and be destroyed almost instantly. It would not last long enough to be observed. This does not mean white holes are impossible. It means they are improbable. The universe is large. It is old. Strange things happen, but in more than a century of astronomical observation, no one has found a white hole. No one has found anything that looks like a white hole. There are no unexplained sources of matter and energy erupting from single points in space. There are no regions that expel everything and accept nothing. The sky is full of sources that emit light and matter. Stars, quasars, supernovae, gamma-ray bursts. But all of those sources have known explanations that do not require white holes. There is no observation that points to a white hole as the best or only explanation. One event that gets mentioned in this context is a gamma-ray burst detected in 2006. The burst, designated GRB 060614, was unusual. Most gamma-ray bursts are associated with supernovae or colliding neutron stars. This one was not. It lasted longer than expected and had a strange spectrum. Some scientists speculated, cautiously, that it might be related to a white hole or some other exotic object. The speculation did not go far. Follow-up observations suggested more conventional explanations. The burst was likely from a neutron star merger or a strange kind of supernova. The white hole hypothesis was never taken seriously by the broader community. It was floated as a possibility, examined briefly, and set aside. That is the story of white holes in a nutshell. Interesting idea, no evidence. Now let's talk about wormholes. The word conjures images from science fiction, tunnels through space, shortcuts across the galaxy, portals to other dimensions. Most of that is fantasy, but the core concept is real. Wormholes are solutions to Einstein's equations. They describe geometries where two distant regions of spacetime are connected by a tunnel. You enter one mouth, travel through the tunnel, and emerge from the other mouth somewhere else. That somewhere else could be far away, light years away, billions of light years away. Or it could be in another universe entirely. The math allows for it. The Schwarzschild wormhole, the one connecting a black hole to a white hole, is the simplest example. But it is not traversable. The tunnel collapses too quickly. In 1988, Kip Thorne and his colleagues at Caltech studied whether you could build a wormhole that stays open long enough for something to pass through. The answer they found was yes, but only if you cheat. You need exotic matter. Not exotic in the sense of rare. Exotic in the sense of having properties that ordinary matter does not have. Specifically, you need matter with negative energy density. Negative energy is not science fiction. It exists. At least, it exists in the sense that quantum field theory predicts it. The vacuum of space is not empty. It is filled with quantum fields, and those fields fluctuate. In certain configurations, the energy density of the vacuum can be less than the average, which is another way of saying it can be negative relative to the baseline. This is called the Casimir effect, and it has been measured in the lab. Two metal plates placed very close together in a vacuum will experience a tiny attractive force because the vacuum between them has slightly less energy than the vacuum outside. That difference is negative energy. The effect is real. It is tiny, but it is real. The problem is scale. The amount of negative energy you can produce with the Casimir effect is minuscule. To hold a wormhole open, you need negative energy on a macroscopic scale. You need it distributed throughout the tunnel, lining the walls, stabilizing the geometry. The amount required is enormous. Some estimates suggest you would need negative energy equivalent to the mass of Jupiter or larger. We have no idea how to produce that. No known process generates negative energy in those quantities. It might be fundamentally impossible. Quantum field theory allows for negative energy densities, but it also places limits on how much you can concentrate and how long it can last. Those limits, called quantum inequalities, suggest that any large concentration of negative energy would be unstable and would dissipate almost immediately. So the traversable wormhole is a theoretical possibility that requires resources we do not have and may never have. That is why most physicists treat wormholes as mathematical curiosities rather than engineering projects. The equations allow for them, yes. But the equations also require conditions that do not exist in nature and that we cannot create with any known technology. Wormholes are possible in the same way that a perpetual motion machine is possible if you ignore friction and thermodynamics. The math works until you add the real-world constraints, and then it stops working. There is another issue. Even if you could stabilize a wormhole, even if you had enough exotic matter to hold it open, you would still have to worry about what happens when something tries to pass through. A wormhole is a shortcut, but it is not a smooth tunnel. The geometry near the throat, the narrowest part of the tunnel, is highly curved. Light passing through would be bent and distorted. Matter passing through would experience tidal forces, the same kind of stretching and squeezing that happens near a black hole. For a small wormhole, the forces could be lethal. You would be spaghettified before you made it through. For a larger wormhole, the forces might be gentler, but you would still need to worry about stability. Any perturbation, any slight change in the amount of matter or energy passing through could destabilize the tunnel and cause it to collapse. You would not get a second chance. Despite all these obstacles, wormholes remain a staple of theoretical physics. Not because physicists think they are likely to exist, but because studying them teaches us about the structure of spacetime. Wormholes push the equations to their limits. They force us to think about what general relativity allows and what it forbids. They raise questions about causality. If you could travel through a wormhole faster than light could travel the long way around, you would be moving backward in time relative to some observers. That opens the door to time travel paradoxes, the grandfather paradox, closed time-like curves, all the classic problems that come up when you start bending the rules of causality. Most physicists think the universe has some way of forbidding these paradoxes, but we do not know what that way is. Wormholes are one of the tools we use to explore the problem. There is also the question of whether black holes could be connected to white holes or wormholes in a way we have not detected. Some modern theories, extensions of general relativity that include quantum effects, suggest that the singularity at the center of a black hole might not be the end. It might be a transition point, a place where the collapse reverses and the black hole turns into a white hole. This is speculative, very speculative, but it is based on serious attempts to reconcile general relativity with quantum mechanics. The idea is that quantum effects, the same ones that create Hawking radiation, might halt the collapse before the singularity fully forms. The collapsing matter would bounce, creating a white hole on the other side. The black hole and the white hole would be connected, and the event horizon would be the boundary between them. This model has problems. For one thing, it predicts that the bounce would happen very quickly from the perspective of an outside observer, which contradicts the observation that black holes appear stable and long-lived. For another, it requires quantum gravity, and we do not have a complete theory of quantum gravity yet. The predictions are tentative, but the idea is intriguing because it suggests that black holes might not be endpoints. They might be passages, not passages you could travel through and survive, but passages nonetheless. Matter falls in, gets crushed and scrambled at the quantum level, and re-emerges somewhere else as a burst of radiation or energy. A white hole that lasts for a fraction of a second and then disappears. Whether any of this is correct is an open question. The observational evidence for white holes is zero. The observational evidence for traversable wormholes is zero. The observational evidence for black holes turning into white holes is zero. These are ideas that live in the equations, not in the sky. They are possibilities that the math allows, but that nature has not chosen to implement, at least not in any way we have been able to detect. And then there is the wildest idea of all, the idea that black holes might be gateways to other universes, not other parts of our universe. Other universes entirely. Separate regions of space-time with their own laws, their own matter, their own histories. This idea comes from the structure of the full Schwarzschild solution, which includes that second exterior region, the mirror universe on the other side of the wormhole. In the math, that region is just as real as our own. It has space, it has time, it has its own geometry. But it is completely cut off from us by the singularity. We cannot reach it, we cannot observe it, we cannot send signals to it. It might as well not exist. Some versions of string theory and other speculative frameworks suggest that our universe is one of many, a multiverse. Each universe is a separate region of space-time, possibly with different physical constants, different particle types, different rules. In some of these models, black holes could serve as bridges between universes. Matter falls into a black hole in our universe and emerges from a white hole in another universe. Or the black hole itself is a kind of bubble, a separate universe branching off from ours. These ideas are fascinating. They are also completely untestable with current technology. We cannot look inside a black hole. We cannot send a probe through the event horizon and get data back. The multiverse hypothesis, if it is correct, makes no predictions that we can verify from outside a black hole. It is a framework for thinking about the structure of reality, not a theory we can test. This does not make it wrong, it makes it speculative, There is a difference. Speculative ideas are not bad, they are necessary. They push the boundaries of what we think is possible. They force us to ask questions we would not otherwise ask. But speculation needs to be labeled as speculation. White holes, traversable wormholes, black holes as gateways to other universes, all of these are speculative. They are consistent with general relativity in the sense that the equations allow for them, but they are not observed phenomena. They are not confirmed by data. They are possibilities, not certainties. And yet, the fact that general relativity allows for them at all is remarkable. Einstein published his theory in 1915. The equations described gravity as the curvature of spacetime. That was strange enough. But buried in those equations were solutions that predicted objects so extreme, so far removed from everyday experience, that even Einstein did not believe they were real. Black holes, gravitational waves, time dilation so severe that clocks could stop, wormholes connecting distant regions of space, white holes expelling everything. All of it was there in the math, waiting to be discovered, and over the course of a century, almost all of it has been confirmed. Black holes are real, gravitational waves are real, time dilation is real. The equations were right. That gives us a reason to take the unconfirmed predictions seriously, not as certainties, but as hints. The universe has a habit of being stranger than we expect. Every time we build a more sensitive telescope or a more precise detector, we find something new, something that was predicted by the equations but dismissed as unlikely. Gravitational waves were predicted in 1916. They were not detected until 2015. Black holes were predicted in the 1930s. They were not confirmed until the 1970s. The universe does not care about our intuitions. It does what the equations say it does, and the equations say white holes and wormholes are possible. But possible is not the same as probable, and probable is not the same as observed. The history of physics is full of ideas that were mathematically consistent but turned out not to describe reality. The steady-state universe, the luminiferous ether, magnetic monopoles, which are still predicted by some theories but have never been found. The equations allow for many things. The universe implements only some of them. The job of science is to figure out which. So where does that leave us? White holes and wormholes are part of the landscape of general relativity. They are solutions to the equations. They describe geometries that could, in principle, exist, but we have no evidence that they do exist. We have no mechanism for their formation. We have no observations that require them as explanations. They remain mathematical possibilities, interesting, provocative, useful for testing the limits of the theory, but not part of the physical universe as we currently understand it. That could change. If someone finds a gamma-ray burst or an unexplained radiation source that cannot be explained by any known process, white holes might come back into the conversation. If someone figures out how to produce macroscopic amounts of negative energy, traversable wormholes might move from speculation to engineering. If quantum gravity, when we finally have a working theory of it, predicts that black holes bounce and turn into white holes, we might have to revise the entire picture of what happens inside an event horizon. Science is not static. Theories evolve, but evolution requires evidence. Right now, the evidence points away from white holes and wormholes, or at least it does not point toward them. And that is fine. Not every solution to the equations has to be real. Not every possibility has to be implemented. The universe is under no obligation to build everything the math allows. It is enough that the equations describe what is there. Black holes are there. Sagittarius A star is there, sitting at the center of our galaxy, 4 million times the mass of the Sun, anchoring the Milky Way with its gravity. The event horizon is there, a boundary where time stops for outside observers and where infall becomes inevitable. The singularity is there, hidden behind the horizon, the place where the equations break down and the known laws of physics stop giving answers. That is the mystery. That is the frontier. Not white holes, not wormholes, the singularity itself. The point where general relativity, one of the most successful theories in the history of science, admits it does not know what happens next. And that admission, that limit, is where the deepest questions begin. Not questions about exotic objects we have never seen, questions about the objects we have seen, questions about what it means for the equations to break down, questions about whether the breakdown is real or whether it is a signal that we are missing something fundamental, questions about what lies beyond the edge of our current understanding. Those are the questions that matter, and those are the questions we have not answered yet. So the equations allow for white holes and wormholes. The math is there, sitting in the solutions to Einstein's field equations, describing geometries that could in principle exist, tunnels through spacetime, bridges between distant regions of the universe, objects that expel everything and accept nothing. The equations say these things are possible, but possible is not the same as real, and real is not the same as useful. Because even if white holes and wormholes existed somewhere in the cosmos, hidden in some distant corner we have not yet observed, they would not answer the question that sits at the center of everything we have been talking about, the question that keeps physicists awake at night, the question that has no good answer. What happens at the singularity? General relativity predicts that the singularity is a point of infinite density, infinite curvature, a place where all the matter that ever fell into the black hole is compressed into a region with zero volume. The equations produce infinities, and infinities are a signal that something has gone wrong, not with the universe, with the theory. General relativity is telling us, in the clearest possible terms, that it does not know what happens at the singularity. It has reached its limit. The framework that describes gravity so beautifully everywhere else, from the orbit of Mercury to the bending of light around galaxies to the ripples in spacetime produced by colliding black holes, that same framework breaks down completely when you push it to the center of a black hole. The math stops working, the predictions stop making sense, and we are left with a hole in our understanding that is as real and as profound as the hole in space-time itself. This is not a small problem. This is the problem, because the singularity is not some distant hypothetical abstraction. It is there, right now, at the center of Sagittarius A star, the 4 million solar mass black hole anchoring the Milky Way 26,000 light-years from where you are sitting, at the center of every black hole in the universe, billions of them. Stellar mass black holes formed from collapsed stars, supermassive black holes sitting at the cores of galaxies, intermediate mass black holes, if they exist, scattered through dense star clusters. Every single one of them has a singularity at its center, a place where the known laws of physics stop applying, a boundary not of space, but of knowledge. The reason general relativity breaks down is that it is a classical theory. It treats space-time as a smooth, continuous fabric that can be curved and stretched, but never broken or quantized. That works beautifully at large scales: planets, stars, galaxies, even black holes, as long as you stay outside the singularity. But at extremely small scales, scales where quantum mechanics becomes important, space-time itself is not smooth. It is grainy, probabilistic, fluctuating. At distances smaller than the Planck length, about 10 to the power of negative 35 meters, space-time stops behaving like a continuous sheet and starts behaving like something else. We do not have a name for what that something else is because we do not have a theory that describes it. What we have are two frameworks, general relativity and quantum mechanics, and they do not fit together. They make incompatible predictions, they use incompatible mathematics, and at the singularity, where both frameworks should apply simultaneously, they collide. This is the quantum gravity problem, and it has been unsolved for nearly a century. Quantum mechanics describes the behavior of particles and fields at small scales. It tells you how electrons move, how photons are emitted and absorbed, how atoms bond and break. It has been tested to absurd levels of precision. The predictions of quantum electrodynamics, the quantum theory of light and matter, match experimental results to 1 part in a trillion. It is the most accurate theory in the history of science, but quantum mechanics does not include gravity. It treats space-time as a fixed background, a stage on which particles move. It does not account for the fact that massive objects curve space-time. It does not describe black holes. It does not predict event horizons. It says nothing about singularities. General relativity describes gravity as the curvature of space-time. It tells you how mass and energy warp the geometry, how objects move through that warped geometry, how light bends and time dilates. It has also been tested extensively. Every prediction it makes, from the precession of Mercury's orbit to the bending of starlight during a solar eclipse to the existence of gravitational waves, has been confirmed. It is one of the pillars of modern physics, but general relativity does not include quantum mechanics. It treats matter and energy as smooth, continuous fields. It does not account for the fact that matter is made of particles that obey quantum rules. It does not describe what happens when you compress matter into a region smaller than an atom. It says nothing about the quantum fluctuations that should dominate at the Planck scale. At the singularity, both theories are needed. The curvature of spacetime is extreme, so you need general relativity. The scale is microscopic, so you need quantum mechanics. But the two theories do not talk to each other. They use different languages, different assumptions, different mathematical structures. Attempts to combine them, to build a theory of quantum gravity, have been ongoing since the 1930s. No one has succeeded, not for lack of trying. Some of the brightest minds in physics have spent their entire careers on this problem. The problem remains unsolved. And then, in 1974, Stephen Hawking discovered something that made the problem worse. He was working on the quantum behavior of fields near a black hole, trying to understand what happens to particles in the intense gravitational field near the event horizon. What he found was that black holes are not entirely black. They emit radiation, not from inside the event horizon, from just outside it. The radiation comes from quantum fluctuations in the vacuum of space near the horizon. Particle-antiparticle pairs pop into existence constantly, everywhere in the universe, borrowing energy from the vacuum and then annihilating each other a fraction of a second later. This happens all the time. It is part of the normal background hum of quantum mechanics. Near a black hole, though, something different happens. If a pair forms right at the edge of the event horizon, one particle can fall in while the other escapes. The escaping particle becomes real radiation. The infalling particle has negative energy relative to an observer far away, and that negative energy reduces the mass of the black hole. The result is that the black hole slowly loses mass. It evaporates. This is Hawking radiation, and it is one of the most surprising predictions in modern physics. Black holes, the ultimate traps, the regions of space-time where nothing can escape, are not permanent. They leak. Over unimaginably long timescales, they radiate away their mass and eventually disappear completely. For a black hole the size of Sagittarius A star, the timescale is absurd, longer than the current age of the universe by many orders of magnitude. The black hole would take something like 10 to the power of 100 years to evaporate. That is a 1 followed by 100 zeros. The universe is only about 14 billion years old, which is 10 to the power of 10. So we are talking about timescales trillions of trillions of trillions of times longer than the age of the cosmos. For all practical purposes, Sagittarius A star is eternal, but in principle it is not. In principle, it will evaporate, and when it does, the singularity will be gone. The event horizon will be gone. The black hole will cease to exist. Hawking's calculation was a bombshell. It showed that black holes have temperature. They radiate like hot objects. The temperature is tiny, inversely proportional to the mass. A stellar mass black hole has a temperature far below the temperature of the cosmic microwave background, the faint glow left over from the Big Bang. That means it is actually absorbing more energy from the universe than it is radiating. It is growing, not shrinking. But in the distant future, when the universe has expanded and cooled enough that the background temperature drops below the black hole's temperature, the black hole will start to lose mass, slowly at first, then faster as it gets smaller and hotter. In its final moments, the evaporation accelerates. The black hole shrinks rapidly, radiating furiously, and then it vanishes in a burst of energy. What is left is nothing, just radiation, just heat. The singularity is gone. The information that fell into the black hole is gone, and that is a problem. The problem is called the information paradox, and it is one of the deepest unresolved issues in theoretical physics. Quantum mechanics says that information is never destroyed. The state of a quantum system, the complete description of all the particles and fields and their configurations, is always preserved. You can scramble it, you can encrypt it, you can spread it out over a large volume, but you cannot erase it. This is a fundamental principle. It follows from the mathematics of quantum mechanics. The evolution of a quantum state is unitary, which means it is reversible. If you know the state of a system now, and you know the laws of physics, you can in principle calculate what the state was in the past and what it will be in the future. Information is conserved, but according to Hawking's calculation, information that falls into a black hole is destroyed. The black hole evaporates. The Hawking radiation it emits is thermal, it is random, it carries no information about what fell in. If you throw a book into a black hole, the book is gone. The information in the book, the precise arrangement of atoms, the text on the pages, the quantum state of every particle, all of that is lost. When the black hole evaporates, all you get back is featureless thermal radiation. The information is not scrambled, it is not hidden, it is gone, erased, deleted from the universe. That violates quantum mechanics. One of the two theories must be wrong. Physicists have been arguing about this since Hawking published his result. Hawking himself initially believed that information is destroyed. He thought quantum mechanics would have to be modified to allow for it. Other physicists disagreed. They argued that information must be preserved somehow, even if we do not yet understand how. The argument went on for decades. In 2004, Hawking conceded. He announced that he had changed his mind and that he now believed information is not destroyed. But his argument for how it is preserved was not entirely convincing, and the debate continues. There are several proposed solutions. One idea is that the information is encoded in the Hawking radiation, but in such a subtle way that we cannot detect it with current methods. The radiation looks thermal when you measure it crudely, but if you could measure every quantum detail, you would find that it carries information about what fell in. The information is there, just scrambled beyond recognition. Another idea is that the information is stored on the event horizon itself. The horizon is not a physical surface, but it has an area, and that area might encode information in a holographic way. This is the holographic principle, the idea that all the information inside a black hole can be represented as a two-dimensional pattern on the horizon. The black hole is like a hologram, a three-dimensional object whose information is encoded on a two-dimensional surface. If that is true, then the information never really goes inside. It stays on the horizon, and when the black hole evaporates, the information is released back into the Hawking radiation. A third idea is more radical. Maybe the singularity does not exist. Maybe quantum effects, the same ones that produce Hawking radiation, prevent the formation of a true singularity. The collapsing matter inside a black hole might reach a point where quantum pressure, a kind of repulsion that arises from the uncertainty principle, halts the collapse. The matter bounces, the black hole turns into a white hole, briefly, and the information is expelled. This is speculative, very speculative, but it is based on serious attempts to apply quantum mechanics to the interior of a black hole. Some models suggest that the bounce happens so quickly from the perspective of an outside observer that it looks like the black hole just sits there, unchanged. But inside, time is running differently, and the bounce happens on a timescale that feels immediate to an infalling observer. The information is not destroyed. It is recycled. None of these ideas are confirmed. None of them are fully worked out. The information paradox remains unsolved. What it tells us is that black holes are not just exotic objects in the sky. They are laboratories, places where the laws of physics are pushed to their limits, places where our theories break down and reveal their incompleteness. The singularity is hidden behind the event horizon, cut off from observation, but its existence forces us to confront the fact that we do not have a complete description of how the universe works. We have two frameworks, general relativity and quantum mechanics, and both are extraordinarily successful within their domains. But black holes live in both domains simultaneously, and that is where the trouble starts. The quest to unify general relativity and quantum mechanics has produced several candidate theories. None of them are finished. None of them have made predictions that we can test experimentally. But they represent the best guesses physicists have about what a theory of quantum gravity might look like. The two most developed approaches are string theory and loop quantum gravity, and they take very different paths toward the same goal. String theory starts with the idea that particles are not point-like. They are tiny loops of vibrating string. The vibrations correspond to different particles. An electron is one vibration, a photon is another, a quark is another. Gravity, in this picture, comes from a particular vibration called the graviton. The strings are incredibly small, far smaller than anything we can observe directly. They exist at the Planck scale, and their behavior is governed by quantum mechanics. Because the strings have size, they do not produce the infinities that plague attempts to quantize gravity using point particles. The theory is mathematically consistent. It unifies all the forces, including gravity, into a single framework. And it predicts that spacetime has more than 3 dimensions of space and 1 of time. It has 10 or 11 dimensions, depending on which version of the theory you use. The extra dimensions are compactified, curled up into shapes so small that we do not notice them. But they are there, influencing the behavior of particles and fields in subtle ways. String theory has been criticized for being untestable. The predictions it makes about the extra dimensions and the behavior of strings are at energy scales far beyond anything we can probe with current experiments. The Large Hadron Collider, the most powerful particle accelerator ever built, cannot reach the energies needed to detect strings directly. Some critics say that makes string theory not even wrong. It is a mathematical framework that may or may not describe reality, and we have no way of finding out. Proponents argue that the theory is too beautiful, too mathematically consistent to be a coincidence. They believe it must be right, even if we cannot test it directly. The debate is ongoing. Loop quantum gravity takes a different approach. It does not assume that particles are strings. It assumes that spacetime itself is quantized. At the Planck scale, spacetime is not a smooth continuum. It is a network of discrete loops, a kind of fabric woven from quantum threads. The loops are the fundamental building blocks, and everything else, particles, fields, gravity, emerges from the way the loops are connected. In this picture, the singularity at the center of a black hole is not a point of infinite density. It is a region where the quantum structure of spacetime becomes apparent. The curvature is large but finite. The density is high but not infinite. The equations do not break down because the underlying geometry is discrete, and discrete structures do not produce infinities the way continuous ones do. Loop quantum gravity makes specific predictions about the structure of spacetime at small scales. It predicts that there is a smallest possible area, the Planck area, and a smallest possible volume, the Planck volume. You cannot divide spacetime any finer than that. The theory also predicts that the Big Bang singularity, the point at the beginning of the universe where general relativity breaks down, is not actually a singularity. It is a bounce. The universe did not begin from nothing. It contracted from a previous phase, reached a minimum size where quantum effects halted the collapse, and then expanded into the universe we see today. This is called loop quantum cosmology, and it is one of the few areas where loop quantum gravity makes testable predictions. Astronomers are looking for signatures of the bounce in the cosmic microwave background, the faint glow left over from the early universe. So far, no definitive signal has been found, but the search continues. Both string theory and loop quantum gravity are incomplete. Both have strengths and weaknesses. String theory is elegant and unifies all the forces, but it requires extra dimensions and makes predictions that are hard to test. Loop quantum gravity is more conservative and makes fewer assumptions, but it has not yet been extended to include all the forces. It only describes gravity. Attempts to add the other forces to the framework have been partially successful but not fully. The two approaches are also philosophically different. String theory starts with particles and tries to build spacetime from their interactions. Loop quantum gravity starts with spacetime and tries to quantize it directly. The question of which approach is correct, or whether some third approach entirely is needed, remains open. There are other ideas as well. Asymptotic safety, a framework that suggests gravity becomes well-behaved at high energies if you allow the strength of gravity to change with scale. Causal dynamical triangulations, a model where spacetime is built from simple geometric pieces glued together in a way that respects causality. Emergent gravity, the idea that gravity is not a fundamental force at all, but an emergent phenomenon arising from deeper quantum processes, the way temperature emerges from the motion of atoms. None of these approaches are mainstream yet. All of them are being explored. The field is active. The problem is hard, and the stakes are high, because black holes are not just curiosities, they are clues. Every time we observe one, every time we detect gravitational waves from a black hole merger, every time we image the shadow of an event horizon, we are gathering data about how gravity behaves under extreme conditions, conditions that do not exist anywhere else in the accessible universe. Conditions that push our theories to their breaking points. The singularity is hidden, yes, but its presence shapes everything around it. The event horizon exists because the singularity exists. The gravitational waves we detect come from black holes with singularities at their centers. The orbits of stars near Sagittarius A star are determined by the 4 million solar mass concentration at the galactic core, and that concentration is a singularity wrapped in an event horizon. We cannot see it directly, but we see its effects everywhere. And those effects are teaching us things we did not expect. The discovery that supermassive black holes exist in the centers of most large galaxies was a surprise. The discovery that the mass of the central black hole correlates tightly with the mass of the galaxy's central bulge was a bigger surprise. It suggests that black holes and galaxies grow together, influencing each other's evolution over billions of years. Exactly how that process works is still being studied. It involves gas accretion, star formation, feedback from jets and radiation emitted by the black hole as it feeds. The details are messy and complex, but the connection is real. Black holes are not isolated objects. They are part of the structure of galaxies. They shape the universe on the largest scales. The detection of gravitational waves has opened a new window. Before 2015, black holes were objects we inferred from their effects on nearby matter. We saw stars orbiting invisible companions. We saw gas spiraling into accretion disks and glowing as it heated up. But we never saw the black holes themselves. Gravitational waves changed that. When two black holes merge, they produce ripples in spacetime that travel outward at the speed of light. Those ripples carry information about the masses, spins, and dynamics of the black holes. The Laser Interferometer Gravitational Wave Observatory detected the first signal in September 2015, and since then dozens more have been detected. Each one tells a story. Two black holes spiraling together, orbiting faster and faster, moving at a significant fraction of the speed of light in the final moments before collision. The merger itself lasts milliseconds. The two event horizons touch, merge, and settle into a single larger horizon. A significant fraction of the combined mass, sometimes several solar masses worth of energy, is radiated away as gravitational waves. That energy shakes space-time across the universe. On Earth, the shaking is tiny. The detectors measured a change in distance smaller than the width of a proton. But the signal is clear. The pattern matches the predictions of general relativity so precisely that there is no room for doubt. Black holes are real. They merge, and when they do, they produce exactly the kind of gravitational waves that Einstein's equations predict. All of this is happening on the stage of spacetime, a fabric we still do not fully understand. At large scales, general relativity works. At small scales, quantum mechanics works. At the singularity, neither works, or both work, depending on how you interpret the breakdown. The singularity is the place where the question becomes unavoidable. What is space-time actually made of? Is it continuous or discrete? Is it fundamental or emergent? Is it eternal, or does it have a beginning and an end? These are not questions we can answer by staring at equations. They require new physics, new ideas, possibly new mathematics, and they require observations, data, evidence that can distinguish between competing theories and tell us which direction to go. Black holes provide that evidence. Not directly, because we cannot probe inside the event horizon, but indirectly through the radiation they emit, the waves they produce, the effects they have on their surroundings. Every measurement we make, every gravitational wave we detect, every image we capture of an event horizon's shadow adds a piece to the puzzle. We are not close to solving it. The theory of quantum gravity, when we finally have one, will not be completed in the next decade, probably not in the next century. This is a long-term project. Generations of physicists will work on it. And black holes will be at the center of that work because they are the places where the need for quantum gravity is most urgent. They are the laboratories where the old theories break down and the new theory, whatever it is, will have to take over. Sagittarius A star is still there, right now, at the center of the Milky Way. 4 million solar masses, an event horizon 12 million kilometers across, a singularity at the center where space-time curvature becomes infinite and the known laws of physics cease to function. We have mapped the orbits of stars around it. We have imaged the shadow of its event horizon. We have measured the flares of radiation from gas falling into its accretion disk. But we have not answered the fundamental question: what is it? Not what is a black hole in the abstract sense. What is the thing at the center? What is the singularity? What happens to the information that falls in? Does it stay there forever, encoded on the event horizon? Does it leak out in Hawking radiation, scrambled beyond recognition? Does it bounce and re-emerge in some distant future or distant place? We do not know. That uncertainty is not a failure, it is an opportunity. The history of physics is the history of confronting mysteries and slowly, painstakingly figuring them out. Newton did not know what gravity was. He gave us the equations, but he admitted he had no explanation for the mechanism. Einstein gave us the explanation. Gravity is the curvature of spacetime. But Einstein's theory breaks down at the singularity, and now we are looking for the next step. The theory that explains what spacetime is made of. The theory that describes the singularity without producing infinities. The theory that unifies gravity with quantum mechanics and tells us what happens when you compress 4 million suns into a region smaller than an atom. That theory does not exist yet, but the fact that we know we need it, the fact that we can identify the limits of our current understanding, is progress. Black holes are not just objects, they are questions, they are challenges. They are the places where the universe is telling us, clearly and unmistakably, that we do not have the full story yet. And until we do, the singularity will remain what it is: a mystery, a boundary, a place where the known laws of physics stop, and something else, something we have not yet learned to describe, takes over. The universe is not obligated to be comprehensible. But so far, every time we have asked it a question and listened carefully to the answer, we have learned something profound. Black holes are asking the hardest questions we have ever faced. The answers, when we find them, will change everything. So here we are, standing on a planet orbiting a star, in a galaxy held together by something we cannot see, orbiting something we cannot touch, anchored by an object so extreme that the laws of physics themselves admit they do not know what it is. 4 million times the mass of our Sun. 12 million kilometers of event horizon. A singularity at the center where space-time stops being a useful concept and the equations produce infinities instead of answers. Sagittarius A star is not just a black hole, it is a statement. A reminder that the universe does not care whether we understand it. It simply is, and what it is, at its most extreme, is stranger than anything our ancestors could have imagined when they looked up at the same sky and tried to make sense of the lights. We have come far. We mapped the stars around the galactic core and watched them scream through their orbits at a fraction of the speed of light. We imaged the shadow of the event horizon itself, a dark circle surrounded by glowing gas, exactly where the equations said it would be. We detected gravitational waves from black holes colliding billions of light years away, ripples in space-time so faint that they moved our detectors by less than the width of a proton. Every test we throw at general relativity, it passes. Every prediction it makes, the universe confirms. And yet, at the singularity, the theory breaks. It tells us it has reached its limit. It points towards something deeper, some structure underlying space-time itself that we have not yet learned to see. The singularity is not the end of the story. It is a door we do not yet know how to open. And on the other side of that door is not just an answer about black holes. It is an answer about what reality is made of, what space is, what time is, what it means for something to exist at all. The black hole is waiting. The question is whether we are ready for the answer. Keep looking outward, because every new signal from the abyss may bring us closer to the language that makes a universe possible.